All right. Hi, everyone, and welcome to the 10th edition of the CV Sports Workshop. So this is a very great year because CV Sports has been running for 10 years, especially at CVPR. So we're really happy to present you with this edition today. So first of all, I would like to show you a bit who the organizers are. So you know that it started all with also Thomas and Rick and also the great people like Graham, Adrian, Jim, who's here today, Michel, and now Sylvia and I, who just joined this year in the organization of the workshop. So first of all, I would like to explain a bit what this workshop is about. So first of all, it is about discovering state-of-the-art work in computer vision in sports. So this is one of the top-notch workshops in the world where you can discover what is new in our field of computer vision in sports. Now, this is also the chance to bring together researchers and industrials who are interested in AI and computer vision for sports. So just I want to know you a bit better here in the room. So by a show of hands, who here is in academia? All right, so mostly people in academia. And who is in the industry? A lot of people in the industry as well. Who are the others who are not in academia or industry? No? All right. So this is your chance now to create collaborations between the two entities. So don't hesitate to network during the coffee breaks and get to know each other because this is really what drives our research forward. All right. So let me give you a few stats about this year's workshop because we have a lot of new breaking records. So first of all, we got 41 papers submitted, which is almost twice as what we used to have in the past. And out of those 41 submitted papers, we decided to accept 24. And this is because there were a lot of high quality papers this year. Because usually the workshop runs around 12 to 15 papers, but there were so many great papers that we decided to increase that number. Out of those 24, 5 of you will be presenting oral presentations, and Silvio will give you all the details about how this is going to work out. And finally, we've got 35 institutions who submitted papers, so who were both from academia and research. So now let me give the floor to Silvio, who will explain quickly the program of the day.
Thanks, Anthony, for this presentation. So today we have a full day of presentations from interesting speakers, from researchers that publish papers in CV Sports. We have selected, as Anthony said, 5 orals that are going to have full 15 minutes presentations for their research paper. And we're also going to have some spotlight presentation for all the posters. We're going to have a poster session as well. And this is the agenda. We're going to start, we're starting already with a welcoming speech from me and Anthony. Then we're going to have at 8:45, so in approximately 10 minutes, Rick, that's going to join us remotely from Denmark and give us an overview of 10 years at CV Sports. She has been working on that workshop for a long time, and she will give us some pretty good insights of what has steered the community over the last 10 years. Then we're going to have a talk from Mersan, that is here with us, from SportLogic, about scalable AI solutions for down market leagues and challenges in youth sports. Then from 9:30 to 10, we're going to have 2 oral presentations. We're going to have a coffee break from 10 to 45. The coffee break is usually a time for us to network, to know a bit more with each other. So we'd like to create an environment for all of us to basically discuss with each other. They will be serving coffee, I think, somewhere where the poster, which I think is upstairs, 4th floor. We are on the 3rd floor right now. Then at 10:45, we're going to reconvene, and we're going to have a talk from Davide Zambrano from Sports Radar. The title will be From Data to Dunk, Unleashing the Power of Metrics in Sports Analytics. And then from 11:15 to 12, we're going to have 3 more oral sessions for the oral presentations for the posters. We're going to have a lunch break at 12 until 1:30. Again, that breaks means networking possibilities, so please interact with each other. Then we're going to have a talk from Mirko Messori from Sfera, who is also the sponsor of this workshop this year. Is going to present Sfera Ground Truth cloud-based infrastructure, the Kings League's use case. Then we received a lot of papers this year, so we decided to give an opportunity for everyone that actually have a poster here to have a 2 minute spotlight, an oral presentation. So imagine that as a very fast pitching about the ideas of their research, followed by a 2 hour poster session. Again, that's a possibility for you to talk with the authors, ask questions. Unfortunately, we won't be taking any questions in this 2 minutes format for the spotlights. Then at 6:45, the people from SoccerNet, from which I'm also involved, we're going to present the challenge of this year, the 2024 challenge, SoccerNet challenges, and the results. We had 4 tasks this year, and we have winners among them, of course. And from 5 to 5:15, we're going to have a Best Paper Award ceremony as well. I'm going to give more information later on. So some practical information. The oral presentation and everything actually will be on Zoom. I'm sorry, the link is not here. I will actually have added, but I didn't have it at that time. For all the oral presentations, please come and test your presentation before your session. Connect with us. We're here for that, and we try to have a transition that are as smooth as possible. For the posters, we have boards from 100 to 123. They are not assigned to any of you, so first arrive, first serve, but we know that we are all from 100 to 123. Okay. The poster must go up at the start of the sessions, 14:45, and we need to take them down at 16:45. Regarding the SoccerNet challenges, we have, as I mentioned, 4 challenges this year, 4 sponsors as well that we thank, Sports Radar, Quality, FIA Technology, and Science NASC, and a total of $4,000 of prize. We also have T-shirts this year, so I'm wearing one right now. Feel free to get yours in the back. We also have a Best Paper Award. So Best Paper Awards means it's a paper published here at CV Sports. It is sponsored by Sfera, and the winner will be decided by the board of juries, from which we actually not part of it. It's mostly the most senior people that have been presented before that have the decision. On top of that, we also have a happy hour organized by Sport Logic. This happy hour will happen tonight at 6 p.m. You need to register in order to join us. And this is a QR code to basically register. I think most of the authors are already registered. There is still spots. So if you want, you can just scan that QR code. We will show that during the breaks as well. And you can join us at 6 p.m. Again, the idea is to create like an environment for people to meet, both from industry and academia, and share ideas and maybe create collaborations for the future. With that, we are done with the presentation, with the welcoming talk. I would ask Rick if you're here. Can you hear us, Rick?
Yes, I hear you, and I'm here. Yeah.
Amazing, amazing. So you're going to give us a presentation of the 10th year of 10th anniversary of CV Sports. I'm going to give you the control. So we can see you here. I think you can share your slides if you can take it from there.
Yes, just give me a second and I will share my screen here.
In the meantime, any questions in the audience? Technical details or practical details I have forgotten? All right. We're here to help. All right. So let me introduce you, Rick. Rick, I mean, doesn't need actually an introduction. She's been the one introducing maybe everyone here in this room. She's been actively working in CV Sports for the 10th edition so far. And today she's gonna give us like a presentation about the 10th anniversary and the story of CV Sports. Rick, the floor is yours.
Thanks a lot, Silvio. Yes, so we thought we would just take the opportunity today to look back just a little bit and on some numbers, some names, some keywords, just to look at the historic perspective of this workshop, because we reached the 10th edition now. So showing here the history, we started back in 2013. with a workshop at CVPR in Portland, Oregon back then. In the beginning, we thought it could be a biannual event. So from 13, we jumped to 15. That was the only time we were not hosted at CVPR, but we applied for ICCV instead, the other main computer vision conference, of course. So we went to Santiago in Chile. And again, in 17, we went back to CVPR. This time, the location actually changed very, very close to that date, but it changed to Honolulu, Hawaii. After that, we saw that there was such a huge interest and a good participation in this workshop, so we thought it could actually happen as an annual event. And CVPR is simply the main event, so we thought about applying for a workshop at CVPR from every year since then. Luckily, the CVPR workshop chairs who decide who's actually going to run workshops at CVPR has accepted us every year, so we are very happy about that. So from 17, we were running in 18, Salt Lake City, 19 in Long Beach. Then a couple of years, which we, on some parameters, just want to forget because it was virtual events. 2020 and 2021, we had these virtual conferences. But then in 2022, again, we could meet again in New Orleans, and 2023 in Vancouver, Canada. And now this year, at least some of you are in Seattle. I'm in Denmark, in Aalborg, but I'm joining you here online. Luckily, that's one of the good things that came out of the COVID virtual break, that we can now join this hybrid mode. So this is the main overview of the workshop. So you already talked a little bit about it. Anthony said a few words about it. Why did we need CV Sports? What was the main motivation behind starting this workshop series? I thought I would just say a few words about that. So first of all, back then we saw an increased interest in computer vision solutions being applied for the sports industry and media as well, because at that time things really started to work. So you could actually take some of this solution, apply it in the media for creating nice solutions, augmented reality, statistics, graphics, and so on that you can overlay, and a lot of analytics as well. And that goes both for media and the sports industry in general, that we need numbers to improve. We've seen that for many years, but it has been human analysts, data analysts, who have been working out these numbers. And that is, of course, a very tedious, time-consuming, expensive job. So why not try to implement some of these computer vision solutions instead, and in a cheaper way, get some of these numbers and insights for your sport. So that was the time to really start to take more of our solutions from the computer vision research and bring that into the industry. From the academic point of view, we also wanted to create a publication outlet where people had a shared understanding of some of the specific domain challenges there are when you apply computer vision or software to sports. Because just a few of them you will recognize is that you will have humans with fast erratic motion, some weird poses. You will have often similar appearances. If you're looking at team sports, they're wearing the same type of jerseys, for example. There'll be heavy occlusions. There are many different challenges that are common to many of these sports types. And that means that we cannot just apply any method and maybe compare to a general data set. It is a little bit special, and we want to have this shared understanding of the domain challenges. And also, there are sometimes some special issues which are very good, but in this case, we wanted to have an event so we could also create a community, allow some networking, share the ideas, and maybe start some new collaborations between people within this field. So as Anthony also said, the real goal of this workshop is really to bring people together, and both from academia and industry. So from academia, we can show what are the current trends, what are we working on in computer vision, how can that be applied to the sports domain. And from the industry, we've always had some keynote speakers, which can really motivate the researchers by showing how the applications are used in industry, or how it's applied in the industry. A few numbers I digged up from previous years I wanted to show you. So as I said, we started back in 2013. Unfortunately, I don't have access to the submissions from the first couple of years, but back then we had 10 accepted papers and 2 good keynotes. It started with actually 2 official organizers. I have the pictures here. So that is Thomas Moslund, that was my supervisor at that time. I was a PhD student. Thomas is a professor from Aalborg University here in Denmark. And then Graham Thomas from BBC Research. They were the official names on this application for a workshop back in 2013. So they were the first 2 organizers. I was taking part of it as kind of behind the scenes as a PhD student. But then we continued in 2015. We now added 2 more organizers, Adrian Hilton from University of Surrey and Peter Carr from Disney Research at that time. They contributed to running this workshop for a couple of years. In 2015, we had again 10 accepted papers, 2 keynotes, and now we have 4 organizers. I also put the number of workshops at the event. So the numbers 19 and 18, that's the number of workshops with accepted papers at CVPR and ICCV. So compared to today, of course, the conferences were smaller. The number of workshops were less back then. Moving to 17, now we suddenly accepted 16 papers, so we are growing. 3 keynote speakers, and now my name came on this workshop. So we are now 5 organizers, and it was also the first year that we had an official Best Paper Award. So here we had the sponsor giving out a prize of $500 for the best paper. Moving to 18, same group of organizers, 14 papers. And in 19, now I have the number of submissions. So here we are at 26 submissions and 14 accepted papers. We had 2 keynote speakers. And then for the organizers, we simply had a substitution here. So Peter Carr switched to a different job. And we had instead Jim Little here. I think you are in the room today. So he has been joining us since 2019. 2020, so the first virtual year, we had only 16 submissions. I think this is the lowest of these in this series. So we accepted 13 papers. Again, maybe that's a high acceptance rate, but we generally have a good quality of papers submitted for this workshop. And what we're really looking for is some interesting papers that we can discuss. So in this case, we accepted 13. 4 keynote speakers, and now we had a new addition for the organizers. So here, Michelle Meller from IBM Research joined us. From 19, we also raised the price. So the Best Paper Award has been $1,000 since then. Moving to 21, we are still the same team of organizers, up again to 25 submissions, only 12 accepted, so that was harder this year. 2022, 28 submissions and 15 accepted papers. Last year we had 27 submissions and 16 accepted papers. And you can also see the number of workshops are growing. So last year, the number of workshops at CVPR was 60. So that is way more competitive now to get some good papers, because there are many different workshops that you can actually send your paper for if you want to go there. And then lastly, this year, we now had 41 submissions, 24 accepted papers, and we are one of the workshops among 72 workshops with papers. Another thing we are really proud of is that we have a duration of a full day for all editions except one. And that is really competitive to get a full day workshop at CVPR, because many are applying for workshops. And also the team has been growing again. So as you saw in the welcome talk, now we have added 2 fresh members to the team. So Anthony Choppa and Silvio Giancola. So they are not new faces. They are the main people behind the SoccerNet Challenge, which has been running for some years now. So they are very experienced guys, and I'm very happy that they could take over and actually be there in Seattle this year, because I had to stay here in Denmark. So also a little look into what are the topics of the papers of this workshop. I took all the titles and tried to create this word cloud, and I think a few things pops out. Of course, sport is the common thing. You will see also many sports types like soccer, tennis, badminton. I have another slide a little bit later mentioning some of the sports that we have represented in these papers. You'll also see some of the aims. So what are we trying to do? Trying to do tracking, finding trajectories, segmentation, detection, camera calibration, pose estimation, and so on. And also there are some words from some of the methods that are being applied, different methods. So what it really is in common between these papers is that we've always had a clear focus on the application. So we are looking for papers which are specifically focusing on sports. And that can be from many different angles, but we are not really looking for for papers which are more general, but can also be applied on a sports data set. We are looking for something that are really discussing some of the challenges and specific things that are related to sports. So if we have a borderline paper, what we're really looking for is it interesting? Is it interesting for the audience which are looking for sports applications? So that's what we really have in common here. Of course, I also had to ask which sports types are then represented in these papers. And based on the paper titles, soccer is clearly overrepresented, if you could say so. And that is the case. Soccer is a very big part of this. But we also had a lot of other sports types. Hockey is one of the big ones, table tennis, and then we have a number of sports, also the smaller ones. So you can see here tennis, golf, badminton, rugby, football, skiing, basketball, baseball, diving, cricket, volleyball, swimming, fencing, esports, darts, canoe sprint, and paddle is a new addition this year. So I think that's a very great thing that we have so many different types of sports. And this is only based on the names that we have in the titles of the papers. I did not dig into the actual content of every single paper. And then just a brief look into what did we actually do back in 2013. Maybe some of you were there. And back then, I just took here a few examples, three of the papers, because the topic is actually pretty much the same. Some pose estimation of the athlete from a 2D image, 3D trajectory reconstruction for table tennis, recognizing team activities for noisy data. The problems look very similar to the problems we're looking at today, but we've come a long way in the methods and the performance of these things. And of course, if you look into these papers, none of these papers from 13 were using any deep learning based methods. So that's a big difference from back then to today. But the topic, the variety of applications and so on are still equally interesting back then as it is today. So who contributes to CV Sports when we're talking about papers? First of all, authors from all parts of the world. We are very happy about that. Many industrial contributions and collaborations. And I found at least 33 different authors who published 2 or more papers in CV Sports. And I'm particularly happy about this because when you come back after publishing one paper and you want to publish in this workshop again, that means that we're doing something right. So we are definitely happy about that. I also want to point out that we have some clear top contributors. Probably you're there today, I guess, Mark. So from University of Liège, we have this excellent group. So Mark van Drogenbroek is the top contributor with 15 papers over the years. And closely followed by Bernard Ghanem from KAUST with 14 papers. And a special thing here is that he published 2 papers already in the first edition of CV Sports in 2013. So these are some of the top contributors, but we have many authors who came back for some years. So just to sum up the future of CV Sports, will we take 10 more years? I hope so. It has become a tradition now to run CV Sports at CVPR actually. And it has got a name as a high-level venue for computer vision research for sports applications. So we are happy to continue at least for some years from now, and we hope to see many of you again in future editions as well. So that was the words from now, and I'm just happy to show this again, that because we're running the 10th edition now, we also for the first time hosting a social event at the happy hour sponsored by SportLogic. Thanks. Over to you again in Seattle.
Thank you, Rick, for the presentation. I feel like we can actually take maybe a question. So I don't know if anyone in the room would like to ask a question to Rick. Feel free to raise your hand and ask the question. If not, I would actually have a question. Oh, there is one. Yes,
Yeah.
Davide, yes.
I was wondering if the fact that the challenges of this workshop specifically are directed and focused on soccer would have biased the submissions toward that specific sport that you were mentioning.
You hear the question, Rick?
Yeah, I think so. Yeah, so that's a good question. Of course, that could be a bias because of the SoccerNet challenge. And also this year, I believe Anthony and Silvio did a little bit of promotion of the workshop, and you have a network within the soccer. But looking back in the first years as well, there was a big influence by soccer papers as well. So I think it has been like that over the years, even before SoccerNet was a thing. But it has been growing in the past few years because of the nice SoccerNet data set and challenge and so on. But I will just if we could have more challenges, more data sets from the other sports, we could have the same type of growth, I think.
Thank you for your answer. Sorry for being guilty about that. We are open to any type of sports. That's fine. Let's do basketball net or tennis net, whatever you'd like to. The question also in the back here.
My question was, I see soccer is #1, but I know it's not even the most popular sport in the US. Is it just because of the market that is saturated in other fields? Because, for example, half-pipe and saturated volleyball or tennis, and it is hard to compete there. Do you think is any reason how market is and why people are working mostly on soccer?
It was a little bit too difficult for me to hear, but
Okay, I will repeat the questions. I will try to translate that question. The question was, do you believe that the reason why the focus was on soccer, why it's not the #1 sport in the US, was it because there is a saturation on other type of sports, mentioning tennis or volleyball, for instance? Do you think this is the case?
That's a very good question. I think it's also something about the availability of the video data, availability of videos, of data sets, who are working on it. We had a lot of European-based researchers, and that is a big sport here in Europe. So it's about who and what do we have. I think some of the other, like tennis is mentioned. There are lots of money in tennis. So maybe they already have some solutions or personal data analysts and so on, while soccer is a little bit more like a community thing. Yeah, I don't have like a clear answer, but there could be many different reasons for that. Yeah.
Does that answer your question?
Thank you.
Yeah, okay, thank you. Okay, let's take maybe a last question here. Yeah.
One question that is related to this, when it comes to tennis against football against how does the sort of level of analytics play in this in terms of like the sport itself? Because at some point I was talking to some tennis player and they were saying, you know, ourselves like 80% of the time we want like do a lot of analytics, but mostly the technique. So once you get the technique right, this is what we need, which means there's less level of analytics. But if you go to football, this is the multi-agent, it's high level of analytics, which means you do need analytics there. So how does this relate to sort of like the sport which is required more technique at personal level as compared to sport that require like more coordination costs like the agents?
Have you heard the question, Rick?
No, sorry, no, it was not clear.
I'll try to reformulate that. Pardon me if like I'm not reformulating properly. I think the question was how does the technicality, the technicity required in specific sports actually correlate with the type of research that is actually involved? Like, for instance, giving an example of tennis. Tennis maybe is only a single agent that will require certain level of technicity or technique that once this is required, that is achieved, you can already like reach some good performances. While sports like soccer or volleyball or maybe American football, let's say, would require more multi-agent kind of approach, which is maybe a bit more complicated, right?
Yeah. I agree that probably in these single athlete sports like tennis, badminton, and so on, there's a clear history of an analyst being able to analyze the games. And in soccer, it is a little bit complicated, but I think there's also an interest in analyzing these because in general you can look at team sports. And soccer is just a good example of a team sport where you have a larger team performing a match against another team. And when you're doing research on things like that, it generalizes. We've seen papers generalized, for example, from soccer to hockey, basketball, some of these different team sports. So maybe it's just a little bit more of a general interest because a lot of people doing that. It is a team sport, and there are a lot of different interesting things you can look at in these types of sports.
Does that answer your question?
Yeah, we go.
All right, thank you. All right, well, let's thank the speaker again. Thank you, Rick, for connecting.
Thank you.
Thanks a lot, and congrats again for the 10th editions of the CB Sports. Our next speaker is Mersan. Mersan is the CTO and co-founder of SportLogic. SportLogic is also the sponsor of our social event this evening. So I'd like to warmly welcome Mersan to join us to give us a presentation, which I forgot the title. Scalable AI solutions for down market leagues and challenges in youth sports.
Good morning, everyone. And how many of you remember this? Okay, this was published in 2011, if I'm not mistaken, way before I started for Logic. And this was a great paper. And it basically showed me that this is possible to do broadcast video processing on a sport events and do player tracking, event detection, and so on. It was published by Jim Liddell, Terry Murphy, and other brilliant folks. Still the same problem. We are still working on this type of problem, but I wanted to bring this up. And this is not working. My clicker is not working. And we have a social event right after this workshop, and I'm going to conclude my talk.
Nice, yes.
If you want to scan that QR code, you have to wait until I finish my talk, then I bring that slide up again. I'm going to talk about how we built some solutions to do analytics in down-market leagues and what challenges we face when we try to kind of go beyond professional leagues, going to the youth sports and democratizing all the analytics tools for all the kind of youth videos that we get. Before going into the technical details, a little bit about SportLogic. We are a Canadian company. We started in 2015. We are the gold standard in the hockey analytics world, and we are data provider for all the major and minor leagues in North America and Europe. A few years ago, we started to do the same thing for soccer and football. When I say football, I mean American football, and when I say soccer, I mean football. So let's say we do football, and hockey. If you watch hockey in North America, US, Canada, and a lot of times you hear about advanced analytics, advanced statistics. Sometimes you see our logo on TV. Everything is coming from SportLogic. We have an active network of collaborators. We actively work with academic research labs in Canada, and some of our regular collaborators are here. And we are open to new academic collaborations. So if you want to talk about getting access to the data, work on some new project, like talk to me or my two other brilliant researchers that will be at the social event, and they are also here in this room. Sport analytics is about insights generated from data. So if I want to talk about at a very high level, there are two parts to it. Part one is data generation. We have to get data, and we need to get information about what is happening in the game. But that's the first step. Second step is to take the data, turn it into actionable insights to be used by coaches for making decisions about how to play the next game, set the strategy, also to do athlete development, and also trade players. Not surprisingly, SportLogic data has been used to
kind of support more than 85% of the trades in the NHL in the past 4 years. Today, I won't be talking about insights because these guys gave me 25 minutes, so I stay focused on data generation part. But if you want to hear more about like what insights we can generate from the data, feel free to talk to me after this. Oh, this is done in a sports data acquisition. Basically, there are different ways. One is take the video, do manual annotation on the videos. And as humans, we can only do few things. So we can mark like high-level things, like interactions, like actions that players are taking, like passes, shots, assists, goals. Those can be marked manually. And manual data collection is still done in the sport world, and it's still a massive part of data collection business. Another way to collect data is to go with variables, passive active localization sensors. And the biggest focus is to not use variables because to put variables on players, you have to get permission from player associations, from the leagues, and you are limited to where you put variables. So you won't get data from transfer market or prospect leagues, so you can't get basic information from venues that you don't have in the market. Computer vision is very interesting. It's been actively used for data collection in sports, and there are different sources of vision systems. Like using multiple cameras in the venues, you can go with like 4. That's the kind of fewest number of cameras that I've ever seen in any commercial system for multi-camera systems, up to 24 cameras to get data from the games. Or you can take the videos that is coming from broadcast cameras, take the single camera feed, one video, or maybe take the panoramic feed, or in soccer, we have the tactical feed that is kind of a zoomed out view of the game, and process that. In different leagues, there are different solutions. Top tier leagues like NHL, NFL, English Premier League, they have money. They have more money than God. So they can spend on anything they want. They can go with most expensive hardware solution. They play a few thousand games, so it's not a lot of games, and they want to have perfect data. So accurate raw data, and some leagues are using multiple systems. Like for example, in NFL, NHL, there's variable, and there is a multi-camera system. So they are combining variables with vision to get all the data they can from the game. And then the game events, when I talk about game events, I mean player actions, interaction on ball or on puck actions. And those are often tagged manually, or they are kind of tagged semi-automatically. An automated system is running, and there is a human verification. And these systems are very expensive because you have to have human watching the game. I remember in the last World Cup, FIFA used one analyst per player to kind of get stats for every single player. So like 22 annotators watching the game in real time. 22 people times 90 minutes. That's how much you need to pay those people. When we go to the second tier league, there are thousands of games happening. And these teams kind of don't have massive budget. They tend to get videos, like everyone reports videos. There are lots of videos, and usually there's one kind of video. Sometimes there are 2 videos in football, like we have end zone, sideline, American football. And they tend to get tracking data often. Sometimes they can get event data, but event data is expensive, and they have to go with cheaper solutions. And these teams also have good domain expertise, but they don't have a big budget like NHL, NFL teams, so they don't have in-house data analysts. They can't have their own analytics team, data science team, so they have to rely on other kind of analytics tools that are built for them. When we go kind of down market, amateur leagues, youth sports, there's really no data. And to do any analytics, you need to have data. And all we see in the youth sports these days is videos. There are videos like streaming services, the cameras installed in many venues. You can subscribe, watch the games, or if you are playing, you can get your video after the game on demand, but all you get is a video of the game. And in those markets, usually there is not kind of domain expertise, no analytical skills, and like the kids who are playing have no idea about sports analytics, but they want to have something useful so that they can improve their performance, they can get better, and they can also see how far they are from becoming kind of a star NHL player. Speaking about top tier pro leagues, like this is the system we developed for NHL in 2018. Uses six cameras, 14 resolution. And this roughly shows the camera placement that we have. The cameras are not anything fancy, like generate 4K, 30 frames per second cameras. We do on-site processing for this system for 3D motion capture, tracking, and we get to 99.9% tracking accuracy. Average localization error of all body joints is less than 10 centimeters. That's a perfect system we built, but it is very expensive, and it's not useful for down-market leagues. They cannot afford to have a system like that. But this shows like what the system does. To say like this is a very old demo. I don't have anything more recent, but the system runs like that. Generates everything in real time. It's 3D motion capture. We tend to do kind of a data collection on all the NHL games. We can have manual QA, and data is perfect. So we kind of get the games, perfect data, provide that to broadcasters, to the NHL teams. The only downside is that we cannot escape this to down market. We cannot go to anywhere that we don't have cameras in, and we have to build a system that takes any videos that is coming from any game, anywhere in the world, and we want to generate similar analytics and similar insights. So that's the problem, as I said earlier, generating comparable data from different videos that we get. And this is kind of type of video that we get from like second tier leagues. Kind of similar to the pro level, like kind of leagues in terms of broadcast, look and feel, but not the same quality, not the same, like it's not the NHL type kind of broadcast. It's second tier, lower quality cameras. Also, the broadcaster is not like, I'll talk about the issues that we see a bit later in this type of video. And when we go and like more down market use, this is the type of videos that we tend to get from cameras that are installed in the venues, kind of a fisheye view of the game. Sometimes we don't see part of the ring. It's kind of partial, and there's a lot of distortion towards the ends, and like near the goals, that's where the most interesting stuff is happening, but we tend to see with fewer spatial resolution. Okay. So when we started to work on this, it was kind of 2-3 years ago, and we wanted to build same thing, like analytics tools for non-market, basically taking a video from a youth games, generate a simple kind of summary of the game, some metrics, impact rating, some of the simplified analytics like expected goal, player heat map for the youth athletes. To solve that problem, okay, let's get back to the basics. Okay, what we need to do to get data from these videos. Step one, in hockey, we have to do game segmentation. Hockey is different than soccer. In soccer, the game starts when the clock starts, continues for 45 minutes for a half. In hockey, we have a stoppage in play. There's face-off, there's whistle. So game stops at the whistle, clock stops, and then there's another face-off. So to have reliable analytics, even if we want to have like player physical data, like distance skated, for example, we want to cut the segments that are not in game. So game segmentation is a part of the work. It's more related to hockey than soccer, but we started with hockey. We love hockey. We are Canadians, so another challenge to take. Then the same kind of tracking problem, player park tracking, which has like detection tracking, player ID, team ID, ID, etc. Which I'm not going to talk about that. Everyone knows how tracking works, and tracking is not a fully solved problem yet. And then event detection, detecting major events, passes, shots, goal, penalties, assists. There are like 40 different types of events happening in a hockey game, but we started to we just started with the major ones and then kind of take it from there. Then once we solve, if we solve these problems, then we have some data, then we can generate some metrics, insights that I'm not going to cover today. Step one, game segmentation. You may think that this is trivial because we have a game clock, there's TV bug in like second tier leagues. So it shows the game time. Why don't you take that and problem is solved? The problem is that game clock in second tier league is kind of noisy. And I'll show you some examples. It is unreliable, it is noisy because it runs manually. And there's a dude sitting in the stadium and he, or maybe she runs the clock. Sometimes forgets to run the clock. Sometimes forgets to stop the clock. The other problem here, like when we are looking at broadcast feeds, like we have partial observation of the game. And like we don't see the whole game. So this is like broadcast, second tier leagues, unreliable game clock, partial observation, but we do have good audio because this is a still broadcast. Audio is a reliable signal. When we go to the youth level, we have a panoramic feed that I showed earlier. There's no game clock, poor audio signal, and the good part, positive part is that we have almost full observation. We tend to see almost all players all the time. So let's look at the game segmentation. How we can do game segmentation? We can go with the visual stream. We can do player tracking, use the tracking stream data, or we can go with the game clock and read the game clock. And I said game clock is noisy. Look at this. Face-off is about to start, but the game clock is not running. The game is happening, like how many minutes, how many seconds? No. They just forgot to run the game clock. And that was a mistake. So if we wanted to look at the game clock only, we kind of miss the whole segment. There might be a goal in that segment. So it's like, we don't want to exclude that. And sometimes issues like this. Picture-in-picture commercials, and sometimes there's a whistle or a face-off happening, but when we look at the, like, we may not see the game clock. Also, we may not know what we are attending to. So we kind of miss that face-off or whistle. But the good thing is that we have different streams of data. We have audio. We have the visual stream, the holistic view. We have the tracking, because we tend to track players for like all the players at once as we see them. Each stream gives us something around like 0.9 F score. And you would be surprised how unreliable game clock is. Like we sometimes like we get 0.75 F score if we run game clock detection, and we tend to miss kind of segments because sometimes people are not running the game clock at the time that they have to. So combining all these 4 streams together, we get close to 0.99 score. Still not 100%, but the thing is that this is like the way we calculate the score is like we give ourselves a few seconds leeway, and we have 100% recall on all the segments. So we are not missing any segment of the game, but we may be localizing that segment a bit late or a bit early. So kind of fusing different strings of data gives us something reliable. Speaking about fusing different type of information, we have tracking, we have the holistic view when we are doing event detection in those videos. We can go with like the video itself, run a 3D model on the holistic video, do event detection, or take the bounding boxes, run a kind of visual feature extractor, go with a transformer or a graph neural net, or maybe run transformer directly on the kind of player bounding boxes, do activity detection. We can do the exact same thing on the trajectory data, XY coordinates of players and the ball or puck that we track, and get kind of activities detected. The thing is that like these two, when we looked at the kind of output of these two systems, we tend to see like the errors are kind of complementary and they can be combined together. So when we start to combine these two, we tend to boost the accuracy a little bit. Speaking about combining different sources of information, when we are doing event detection, mostly in hockey, we have to also look into combining like visual information with other streams, maybe pose, because there's a difference between making a pass or taking a shot, the way the player handles the stick. So if you don't watch hockey, players are playing with a stick, and the way players are handling a stick, I think for different actions, they tend to move their stick differently. We've done some kind of work on combining like visual stream with pose, and kind of we got good results by doing a late fusion between pose data and visual stream to do activity detection. I have to go over this quickly because I'm kind of running out of time. But the message here, like take-home message for this is like for processing these videos and getting event data, we cannot take the video itself simply and run something like a 3D model on that. We need to use all the streams of information we have, combine them. So like take trajectory data, body pose data, and the whole visual models all together, then do a fusion at the end. Like often late fusion gives us good results. And when we combined all these 3 separated streams, we got close to 0.15 the score boost for event detection. This one shows running these models on youth videos, that panoramic fade, but we crop it to show like kind of a broadcast so that you can see the action. This shows what the model predicted and ground truth for shot attempts. This is the happy path. Everything seems to be perfect. Detections are aligning perfectly with ground truth. Everything looks good. So to conclude, what we had to do to extend everything to down market, because we have partial observation, because we have incomplete signal. Single stream methods didn't give us what we really needed in terms of accuracy. So we had to use all types of information that we could extract from videos. We have the tracking, like we have to do player tracking because we need to know who the players are, where they are throughout the game. So that's one stream. The whole video itself is another stream. And we do have body pose, and combining all these 3 give us something acceptable in terms of quality of the data detected from the videos. And seems that whenever we don't have kind of multiple sources of videos, like going with the kind of multi-stream detection and multi-stream fusion, combined with some attention mechanisms, give us some performance boost and gives us acceptable data for a sports application. All right. I don't want to say that we solved the whole problem because there are still challenges, specifically in the youth market and like third-tier leagues. We tend to have kind of the input distribution changes because we are not getting same type of videos. Videos are evolving over time. Also, there are edge cases that are not recoverable. When we have poor video quality, there is no way to detect puck, to track puck, to detect track player, like that example. Like when we have carpet fit, we can't do much. We are limited to what we see. We are limited to what we get. And these are the problems that cannot be solved by kind of visual perceptual systems. When we have missing footage, there is nothing we can do. When there's picture-in-picture, probably we can solve that problem, but we have not kind of put any focus on it. And when there's bad camera placement, that's a very bad thing. Like sometimes I've seen, like mostly in kind of second-tier Swedish leagues, they tend to put camera in one of the corners. And say, yes, good. You see one side of the ring quite well, but on the far side, you don't see anything. And the camera is placed so low that it's like everything is blocked on the other side of the ring. And you don't see much and you don't get much. And every time we cannot process some of those videos, some of our clients complain. It's like, oh, I want data on my team. It's like, yes, but just move the camera a little bit. One other thing that is happening in youth sports quite often is that these kids are talking in their jerseys. So when they talk in their jersey, half of the number is gone. We don't see the bottom half of the number. We don't see, we can't identify, we can't track. So that can be solved by doing a little bit more education, but other problems are still challenging. Okay. I was about to conclude the talk, but there are still other challenges. So what I've showed you with a kind of multi-stream processing, we kind of made CV work for youth games. We got the data. So it's like, aren't we done with this problem? Can we move on? It's like problem solved. The reality is that the problem is not solved. Yes, we dealt with the data generation problem. So we process the videos, we get the data, we are well above 90% in terms of data accuracy, but we are limited to what the camera says. And if we want to have any useful analytics insight, we need to have a kind of uniform and reliable input data. We cannot go with like 90% accuracy on the observable part of the video and throw like the pro-level analytics models, like inverse reinforcement learning models, and then come up with like impact rating for the players, because that amount of missing data cannot be handled by our models that are built for perfect full data. Also, another big challenge that we are facing and we are working on is like, what is relevant in the pro sport is not necessarily relevant for the youth users. Youth kind of users don't have the sport knowledge, don't have the analytics background, and educating them takes a long time, but we can invest on educating them, kind of making them understand what analytics means. But in the meantime, we have to give them something that is useful for them and they can kind of use and evolve and become better. When I talk about like data incompleteness and inaccuracy, there are issues that we are still facing. A pass towards the net is identified by our model as a shot attempt. Yes, it looked like a shot attempt, but the reality is that there is a difference in a pass towards the net and the shot attempt. And when we are applying kind of impact rating models, like these are different, completely separate types of events. They have different values. So we cannot mix them. We cannot say, okay, like this was a shot and that was kind of the expected score for that. No, that was not. That was a pass. And the player was trying to make a pass. So our analytics models are not necessarily going to work out of the box on this. And sometimes when we go to the very kind of low age group, due to the pace of the game and small size of the players, sometimes the model doesn't pick anything up. So there was a shot attempt that the model completely missed. And you cannot miss any shot attempts in a game. Because like a kid tried to make a shot, and that shot has a value. Okay. Yes. So what we are doing right now at S4Logic and what we are kind of trying to solve these days, we need to generate complete data from partial observations. And by partial observation, I mean like what we see in the camera, like we are limited to what we see. For example, in soccer, it doesn't matter whether like it's second tier, third tier league, like if it's broadcast, we are limited to what is happening in the broadcast field of view. But if we want to generate physical metrics, or if we want to do any player performance metric about like how much they are contributing to the outcome of the game, or whether they are at the right location at the right time, we need to do a good location estimation. So we tend to use generative models to generate location data for players when we don't see them. This way we can generate physical data. This way we can use full analytics model. And there are segments that we don't even see in the camera, but still we tend to kind of do location estimation for where players are. And then now we see the camera is back and we have tracking data for the players. Also, when we do game event detection, we are missing some events. We misidentify some of the events. For example, a pass is misclassified as a shot attempt. And in the youth market, we cannot do manual QA. So we have to take partially accurate data and incomplete data, and then generate a complete sequence of the events in the game, a plausible sequence of on-ball, on-puck action, and then use that whole sequence combined with full tracking data to come up with reliable metrics for the players. So next thing that we are working on is kind of the two streams of data that we have, the kind of continuous stream of tracking data, a discrete sequence of events that are happening in a game, and generating a complete sequence of the game events plus player tracking data, so that we can feed our kind of models, game models with this data and generate insights for the player. So if you are interested in these types of problems, feel free to talk to me, talk to Siavash or Bahar from S4Logic, and we can talk about more details about how we do this. And maybe if you are interested to work on these types of problems, there's a place for you at S4Logic.
Thank you.
As I promised, that's the QR code.
Thank you very much, Mersan, for your very interesting talk. So before we move on to the next talk, do we have any question in the audience? I know I've got a lot, but yeah, let's give the priority to the audience. Yes, please.
Thank you for in your company system in the multi-digital game, the use of how many hours will you take to complete to game complete tracking and event?
How many like
Hours.
So you are talking about SLA for processing?
For cluster.
Okay. So our processing, like we are not processing anything live for new games because there is no live requirement. No one wants live data because a lot of times players are watching their games and they want their summary start right after the game. We have let's say 15 to 20 minutes turnaround time.
So, by the complete, directly with manual correction.
Oh no, there's a like when I'm talking about like second tier youth, there is no human in the loop because like these leagues they cannot afford to like or like they cannot afford to pay premium for like complete data. So we cannot do any manual QA. So manual QA on kind of game events like is happening at the NHL level, like top tier, like we have manual QA. When we go down market, everything is fully automated. So that's why the turnaround time is very fast. Everything runs on the cloud. So no human intervention whatsoever. Nothing.
Thank you.
Thank you, I think we have another question there in the back. Yeah.
I was wondering what you'd say the budget would be for each level of each tier. So how much a single pro level team, second tier team, a down market team can pay for camera system, like in dollars maybe.
Okay. Camera system and data are a bit different because like if I want to say like when we go from NHL to kind of second tier leagues, the analytics budget for the second tier leagues kind of 1/10 or 1/20th of the NHL teams. And when we go to the third tier league, it's like we are talking about like maybe 1/50th. So like and when we are talking about youth, it's like it should be like few dollars per game. We like even though like less than $10 per game.
Thank you. I think we got another question there in the back.
Hey, great talk. I was wondering with, you mentioned the term manual QA, the down lead. How do you deal with model improvement there? Is it internal QA that your team's doing for improving the model? Or do you have ways of getting feedback from the customer that allows you to get more crowdsourced data points?
Oh, that's a very good question. We do have a lot of metrics that we tend to track for the quality of the data. Like, for example, we know we can let's talk about like tracking. We know how many players we should be able to track, what percentage of the players should be kind of identified by reading the jersey numbers, what would be the distribution for like ReID features, etc. So we have a lot of internal metrics that we track, and then if we see any degradation in the performance, we look at the videos and then maybe do some manual kind of QA on those games, add them to the training mix. We tend to like early on, we had to do more of that, and as we got more coverage of the games, like the need is kind of almost none. So much like I think we have not touched our youth models in about a year.
Yeah,
so far. Like we got a good distribution so far. So like everything is kind of within that distribution. But the moment we go with kind of a different streaming service and different camera types, different placement, or maybe like a different country with different ice rink sizes, and then we need to do some tuning on the models.
All right. Thank you very much. So if you have any more questions for Mersana for Sports Logic, you have all coffee breaks and also the happy hour at the end of the day. Thank you. Thanks once again our speaker. And now I will introduce our first oral presentation of paper of the day. So let me introduce Lauren Okamoto from Princeton University. We're going to do a talk on hierarchical neurosymbolic approach for action quality assessment.
Yeah. What is good? What is yours?
So you will have time to ask question after Lauren's presentation as well.
Good morning. My name is Lauren, and I'm here with my co-author Paratosh. We are excited to share with you all our work on presenting a hierarchical neurosymbolic approach for comprehensive and explainable action quality assessment. So to explain a bit on what action quality assessment is, it's fascinating because you not only have to recognize what an action is, but you have to quantify how well an action was performed. And this is seen a lot in sports, such as dance, figure skating, gymnastics, diving, but it's also seen in non-athletic actions such as painting, drawing, surgery skills assessment, and rehabilitation exercises, etc. And so for a little bit of background, I want to explain a bit on how scoring in diving specifically works. And so dives are given a score from 0 to 10 points, and each phase of the dive must be scored with equal importance. And what I mean by this is that a dive can be segmented into 4 different phases. So the start, takeoff, the twist, the somersault, and the entry into the water phase. And within each phase, there are performance factors that are considered, such as the jump height, the distance from the platform, the position tightness in the twist and the somersault, and the splash size during the entry into the water. And all of these phases must be weighted equally when a judge gives their score. So with that in mind, I do have a question for the audience. This dive was performed in the London 2012 Olympics, and I want you to think about which of these 2 scores is more fair. So score 1 is a 9.7 out of 10, and score 2 is a 5.7 out of 10. I'll just give a few seconds to lock your answer in.
Yeah.
All right. So by round of applause, who thinks that score 1 is more fair for this dive? Who thinks that score 2 is more fair for this dive? Great. So if you did choose score 1, this score was actually predicted by a fireworks action quality assessment model. And we believe that this model gave this dive an almost perfect score because of its very, very good entry into the water. The dive was vertical and they made very little splash. If you chose score 2, this score is actually predicted by our proposed neurosymbolic AQA model. And you might be wondering why the score is lower than score 1. So our model actually found performance errors in the beginning of the dive, such as the feet coming apart on the takeoff and twist, the low jumping height off the platform from the start, and also during the somersault, their position was loose. And so our model was able to more fairly account for all of the aspects of the dive instead of overemphasizing the entry phase or the splash. And it actually was able to catch errors earlier in the dive that the human eye might have missed. From the video that you saw, you might not have seen that the feet came apart or they had a loose position in somersault. And this ensures that athletes are objectively awarded, or in this case, penalized for all of their performance from the start to finish of the dive. And for the rest of this presentation, I want to go over sort of how our model works, why it's more comprehensive and explainable. So existing AQA approaches are purely neural. And what I mean by this is that there's a video of an action, you pass it through a neural network, and this neural network is trained to predict a singular AQA score. And so this approach is black box in that there's no explanation as to how this score has been calculated. And so the drawbacks of this overall approach is that the model learns to score with the same biases as human judges, as the human judges' scores are subjective. There's no transparency as to how the score is calculated and what factors were considered, and it lacks explainability and trustworthiness because of its black box nature. And so we proposed a neurosymbolic approach to AQA, which basically means that instead of the neural network directly outputting an AQA score, we instead trained a neural network to output interpretable symbols. And we apply rule-based AQA on these interpretable symbols in order to predict an AQA score. And so the advantages of this approach is that now our model is interpretable and transparent, so white box as opposed to black box. It's data efficient in that we do not need to train this system over a very large number of videos with human labeled data. And it's flexible in that we can change the rules without needing to retrain this entire network. So we create a scoring system for competitive platform diving in order to demonstrate this approach to AQA. The first step is to abstract the interpretable symbols, and in competitive diving, this means the platform, the diver's pose estimation, and the splash. And we had to hand annotate several hundred frames in order to train these neural networks, and all of this data will be available at this GitHub link. After we are able to abstract the interpretable symbols, we apply rule-based programs in order to do the following tasks. The first is temporal segmentation, and this is basically just segmenting the dive into its 4 different phases. And we're also able to do fine-grained action recognition, which just means recognizing or classifying what the dive is. So in this case, no, it's not an arm stand, its rotation type is backwards, it's in the pike position, and the number of somersaults and number of twists are 2.5 each. And I do want to go into a little bit intuition on how these rule-based programs are developed. And so let's look at the somersault counter, for example. We track the pelvis to thorax vector, and this vector is calculated from the symbols that we abstracted earlier, particularly the pose of the diver. And we see that the number of times the thorax rotates around the pelvis directly correlates with the number of somersaults the diver has performed shown in the graph on the right. And so once we are able to develop these or graph these solutions, we're able to code it into a rule-based program that is used directly in our system. And so this overall flow is not only used for the somersault counter, but all of the tasks for temporal segmentation and for fine-grained action recognition. So once we're able to do these 2 tasks, we're able to apply more rule-based programs in order to do action quality assessment. And in particular, we look at 9 different errors of the dive, and we are able to quantify them or the performance of them by doing something called percentile scoring, which I will explain now. So let's just take the feet apart error. For example, over this dive, we calculated that the diver's feet apart were approximately 5 degrees on average for the duration of the dive. And when we plot this on the distribution of all Olympic and World Championship dives in our data set, we see that 5 degrees is only better than 22% of the dives, and in which case we score it a 2.2 out of 10. And so using the percentile scoring, all other errors are quantified, and by averaging all 9 of these error scores, we're able to get an overall score for the dive. And so now we're finally able to generate a detailed score report summarizing the performance of the dive. And we detail each error, all 9 of them. We have a description for each of them, and we also show visual evidence in the form of GIFs. And by averaging the scores on the right, we're able to get an overall score that's shown at the top. It's a little hard to see, but it's 5.7. And so just to recap, this is the overall flow of our system. First, we abstract the necessary symbols from the video data. Then we're able to do temporal segmentation, fine-grained action recognition, and action quality assessment, from which we are able to aggregate these individual error scores into an overall AQA score and also generate a detailed report. To evaluate each step of our system, we start with temporal segmentation and fine-grained action recognition, and we see that our model performs better than state-of-the-art models previously. And we do want to emphasize that no training data was needed to achieve these results. For action quality assessment, the evaluation process looks a bit different. So because we propose a new objective way of scoring dives, our generated or predicted AQA scores are expected to be different than the actual scores from competition. And so without these ground truth labels, we decided to do an expert survey. And so we surveyed a group of domain experts and showed each expert 50 dives, and they either agreed or disagreed with the dive's overall score and individual error scores. And we see that the agreement is actually over 90% for all components, which is a very promising result. We also interviewed two particularly qualified experts, one of which was an Olympic diving coach, and the other was a certified judge on the judges commission. And the Olympic diving coach believes that our system would be useful for the following things. So teaching judges how to score, catching errors that a human judge may miss, settling disagreements between judges, and encouraging safety, maybe most importantly, by penalizing the dangerous actions. And so the certified judge also emphasized that last point of encouraging safety because of the automated distance from platform measurement. We also do a quantitative comparison to the neural approach. Purely neural approach. And we see that domain experts actually prefer our output 96% of the time, which is, again, a very promising result for our model. We also do a qualitative comparison to this same model. And you might remember this dive from the beginning of the presentation. This was our actual output from our model. And so the dive in the beginning was loose and sloppy, but had an extremely good entry. And so our score sort of averages that to a pretty average score of 5.7, while the neural model score is significantly higher, which suggests that the neural model was biased towards the entry phase, unlike our model that sort of accounted for all of the phases of the dive. So to conclude, we propose a new neurosymbolic paradigm to AQA that is objective, transparent, fair, and explainable. Our model achieves state-of-the-art performance for temporal segmentation and fine-grained action recognition. And our AQA scores were verified by a group of domain experts, including an Olympic diving coach and a certified judge on the judges commission. Our generated reports are useful for many things, such as teaching judges, catching errors, settling disagreements, encouraging safety, and training athletes. And we want to conclude by saying that we believe that our model has broad applicability, so that the neurosymbolic approach to AQA can be extended to other sports, such as figure skating or gymnastics, or other critical domains such as surgery growth assessment. Thank you so much for your attention. Two last things, please visit us at our poster if you have more questions. And we also have a demo on Friday in Arch 4C. So if you want to talk to us then as well, that would be wonderful. But thank you so much.
Thank you very much for the excellent talk, Noreen. So we'll take questions from the audience. Yes, David.
I was wondering, so you mentioned that the neural network is biased toward probably the final phase of the dive. I was wondering, if you would train the neural network over your AQA and AQA, would you get fair neural network quality?
That's what we think, because our scores are sort of accounting for all the phases of the dive. We think that instead of training the neural network on those maybe the subjective human scores that might only really see the entry phase of the dive, we think that training a neural network on our scores would potentially help mitigate that bias. Yeah.
Okay, we have another question. Yes.
When you were talking to the experts in the field, I guess aside from the fact that your model really works better than the other one, did you find that they were also more, I guess, accepting of the idea of having an AI scorer because they could understand better how it was reaching its conclusion? And like, from an applicability perspective, I don't know,
I think
any evidence there that it might be more like willing to be accepted as a backup for judges?
I think that there were mixed results, but they did like the generated report because, like, I guess almost as an assist to human judges. I think like completely replacing human judges with AI was something that I think needs a bit more time to open up to. But I think being able to see sort of all of the errors like highlighted and laid out was something that was very helpful. And for the reasons that I said in the talk, I guess. I think it could be useful for that reason.
Got another question there.
Did you test the robustness of your model versus the neural net on the angle of the camera or other aspects of the video?
That's a great question. So we just use the fine diving data set, which I believe has dives from the I want to say like Olympics, World Championship sort of level. And so those are all filmed from, I guess, like way back from like the where you sort of like have the diver on the side and we follow the camera. So we don't have videos or we didn't have the data where maybe like the judges are sitting on the ground and they're sort of looking up. So I think like that's like a next step for us is that we need that a little bit more robust in that way.
Got a question up front.
Is there a question, does the camera actually move here and track players, or is that the diver, or is that a cutout from a static camera?
No, the camera actually tracks. I believe I think it's someone behind and sort of like moving the camera.
That introduce my robustness.
Still got a bit of time for questions if you want. Otherwise, I've got a question. So I found your work very interesting. And I was wondering, like, somehow deep learning went from handcrafted features to or like learning abstract features, and then your approach is taking back these kind of trying to figure out what are the best things to add to the model. So what's your take on this question? So like, how do you see that that shift of representation that goes back to what was been done before, but scores better than all the neural architectures?
I do think it's interesting. I know like the neural approach has its own benefits of like you don't need that human or domain expertise in order to like formulate these rules in order to actually like do this model. I think both approaches have their own positive like positivities. But no, I think it's very interesting that like almost stepping backwards like from the very deep learning approach that this actually does better. So yeah, I think it's something that I need to think about a little more as well.
And can I add something to
Yeah.
that?
Yeah.
So we actually use the strength of both the approaches. The symbolic approach actually does the processing
Mhm.
in a more logical way and more domain oriented way. But we do actually use neural networks for perception because that's their strength. So it's not choosing any one of them, but choosing the strengths of both.
Very interesting. Okay. So if we do not have any more questions, let's thank Lauren West again. All right. So let me introduce now James J. Clark from McGill University, who will present work of video interaction recognition using an attention augmented relational network and skeleton data.
Thank you. All right, thank you. So I'll be presenting the talk today, but this is work of my PhD student, Bea Ascari, or Zena Ascari. And in the introduction, Rick had talked about people who had papers at many of these workshops. I would just point out that this is her third paper at this workshop, which is a regular. Unfortunately, she wasn't able to get a visa to come. So I'll be giving the talk. So we want to talk about a method for doing action classification. In particular, we're going to apply it to the problem of classifying actions in hockey games, in particular, classifying penalties, which are an activity within hockey games. And in general, of course, you all know that understanding human interactions is important for video understanding. So a lot of the actions that we're interested in sports are actually interactions between players and their environment. And our approach, which we've had in the last couple of papers in these workshops, are focused on using skeletons as the main features rather than the iconic images.
we want to look at just using the pose for the information. And there's a number of reasons why we want to do that. One is that this is a very concise representation compared to the images. And this saves us, processing time and so forth. It alleviates some scene biases. We won't go into those, but it can help with those issues. And also it reduces privacy concerns because the skeleton representation hides a lot of personalized information. For Sam talked about youth sport. Maybe there's some issues about privacy when you're talking about use and so forth. So the approach I want to talk about today, we're modeling coarse interactions between individuals. There's fine discriminative relationship between their body joints. Okay, so we have key points in our skeleton. We have coordinates. We can use those as our features. Okay, and the motivation for this approach is that we can think of video action recognition as a relational reasoning problem, and we can employ what are called relational reasoning networks. So relational reasoning networks, or we call them RN, were first introduced by Santoro et al. In the paper in 2017. Okay, not for hockey, but it's for other things. And it has the formulation shown here in this functional equation here, where what we have is the output of the network, which would be a classification in our application, takes in a set of objects, and we can define these objects in different ways. We'll show a particular definition of these objects in this paper. And we have a pair of these objects. So we're looking at relationship between these objects. And we have some function. This is going to be a trainable function, g theta, a parameter theta, which we learned. Typically, it's going to be a neural network of some sort, okay, which is learning the relationship between these. Then we have an aggregation operation. We're sort of combining multiple of these, which takes different objects. We have multiple objects in our representation. Okay, so we have an aggregation between these. And then we have, after the aggregation, we have a set of features we're going to pass into our final network, say, to do classification. So this F theta could be a classifier, for example. Okay, and these are learnable. These functions F and G are learnable, and the objects we define what those are. Now, it should be noted that the key point of this relational approach is that we have pairs of objects, but these objects can be quite different depending on what your application is. So we're going to propose basically a method for doing this classification of these sports-related actions, okay, using this general approach. And it has a number of nice features. We call it AARN. It's easily extendable. We can define different types of objects, or more objects, or fewer objects. Flexible, fusing multiple modalities. They just have to be vision or joints. We can use other modalities. In this paper, we're just using joint information. It's extendable to multi-person videos without significant cost. Our approach today, we're just mainly focused on two-person interactions, but the representations that we described can be extended to multiple, more than two people interaction. And also, this is a computationally efficient approach, say, compared to a transformer based approach. And we'll see how that works. So the first step, we want to say, well, what are the objects we're going to use in our relational network? And we're going to base our objects as features from the joint information. So we're going to assume for now that we have a pose that's been estimated. Okay, we have video of people, we extract joint information, and we'll leave for now how that's actually done. Okay, so we have these joint information, and we're going to look at, in this application, pairs of joints, okay, for two people. Because the interaction we're mainly interested in for this application for hockey analysis, we're looking at sort of these binary actions where we involve two players. And in particular, we're going to be looking at penalty classification. Like, is there a penalty? And if there is a penalty, what type of penalty is it? So typically these penalties, unless you have a bench clearing brawl, just involve two people. Yeah. So we have our object here. We're going to define them as a vector, basically, of the key points, the coordinates of the joint locations. Okay. And we're going to have two sets of key points for each of the two players that are involved. Okay, so we have the X, Y, Z for the joints for player one, the X, Y, Z for player two, and then we have a time we keep track of which time frame this is from, because we're looking at videos, so we have a series of video frames. Okay, but we're going to look at one video frame and and form an object from that. But note that the relations that we're going to be talking about, remember this relational network approach computes relations between two objects. We're not looking at a separate object for each player, but we're combining the representations for each of these two players in a single object. And the relations that we're going to be looking at are relationships from one frame to the next. And this provides us with a way to embed the sequential or the time varying information. And we can avoid using things like recurrent networks or LSTMs and so forth, or even transformers to do this. And this results in a more efficient approach. Okay, so this is the first step. We define these objects. Okay, and now we want to pair these objects because we're looking at the relational aspects. And we make a number of relations. We're not just looking at a single relation. We'll look at many relations. And so what we do is we take two frames. So here we have our object one, which contains this vector of joint information from the two people that we're interested in. And then we have another frame. Okay. And what we do is we create another object or another representation where we combine these. So we have, say, object one, object two, and we're going to append to these what we call relational features, which is indicated by H here. We'll get what those are, just some added information. Okay, so we call this object pairing and expansion. So the relationships that we're looking at, for example, are relationship between object one and object two, which are these pose vectors for the two people at two different frames. Now, if we have, say, T frames in a segment of video that we're looking at, okay, we won't talk about how we segment the video. Think of having a moving window, which is looking to detect penalties. Okay, we could have many different pairings. We could compare object one with object two, or object one with object T, okay, and object two, and so forth. So we get a list of these, which sort of goes quadratically with T, but T would be relatively short. Okay, so this is sort of the first step in our relational function that we showed at the beginning. Okay, and this is what we feed in. Okay, now what we do is we also augment the object pairing with what we call this expansion, which we call relative or relational features. And these are basically just looking at relationships between the two skeletons within an object. And I think we have a slide on what those are. Yeah. So we actually define three different types of these relational features. So it's just added information, which is added to the joint information. And what we're doing is these are relational features between the two objects. Okay. So we have three types. The first type on the left is basically a distance between the two actors within each frame. It's an intra-object measurement. Okay, so we just measure the L2 distance between these joints as a vector. Okay, and then we concatenate those to give output D. Okay, so it's basically just saying how far apart the two actors are in each frame. The middle one we call M. Okay, is a movement. It's basically saying how does the one actor move from one object to the next or one frame to the next, to give some sort of motion information. Okay, and again, we do that for each of the two people within the object, and we concatenate those. So it's basically a motion vector. And the third one is sort of an intermotion between the pairs, okay, which is looking at, you know, say actor one and actor two, but in two different time steps. Okay, so it's sort of a higher level second order type of motion. So we create these extra features, called these relative features, or relational features, and we have there are another three vectors that we append to the two objects vectors that we have. Okay, so recall the original formula we have of the relational network. Okay, we have our O, T, OS, these are the two objects that we're comparing. And then we have this additional information. Okay, this extra features. Okay, so what we want to do now is to have a network which is learning this function GS. And then we follow this with some aggregation. Okay, and the networks that we use are actually very simple. They're just simple multi-layer perceptrons, typically 3 to 5 layers. I think we use 5 layers in the experiments we're talking about. Okay, so we pass these through a relational reasoning module called G theta. So these are all trainable. Okay, but they're very simple. They're just they're not deep. They're 3 to 5 layers. And now we want to aggregate these because we have many of these G's. Okay, because we have these different pairings that we're looking at of our objects, which compare different frames. Okay. Now we want to aggregate these somewhere. Now we could just add the outputs of these together. Okay, the outputs of the G's are going to be some embedding or representation. Okay, we can just say average those. That's one approach. But what we want to introduce here is an approach based on attention. And we're going to use this similar type of attention mechanism as in transformer, sort of scale dot product attention. You can see on the right-hand side the typical dot product attention approach found in transformers. Okay, so this is not a transformer. We're just using this approach just to, do it basically a weighted, learnable attention for focusing of our aggregation. So it's for determining which of these sort of relations are most important or relevant for classifying a given type of action. Okay, and again, this is learnable, these aggregation weights. And finally, once we have that, we pass it to our last network, which is just again another multi-layer perceptron, 3 to 5 layers, acting as a classifier, probably 3 layers. Okay, so that's the approach. So I want to talk about now how does this work and how we apply it. We're going to apply it to what we call our hockey penalty data set, which student Faye talked about in the previous 2 workshops that she attended. And these are clips of hockey penalties from NHL broadcasts. And we actually have for many penalties, but this particular subset includes examples of tripping and slashing. So those of you who are not hockey aficionados, tripping is, where you have 2 players and you have the stick, as Merced said, we have a stick. Okay, we put the stick in the legs and we trip the player. Or slashing is where you take the stick and do something very Canadian. Okay, so they're somewhat different. So you expect we should be able to classify these versus hooking, which is rather similar to slashing. And also no penalties, sort of the default class where no penalties occurring. So we want to classify based on the videos coming in. Okay, and we look at these videos 2 to 6 seconds in length. And we assume that we have annotated body skeletons. And we'll say a little bit of how we get those and the effect of the quality of those. And we're also going to annotate the hockey stick. Okay, so in addition to the joint locations, we're going to add sort of position of the top end of the hockey stick and the far end. Both of these actions, the hockey stick actually plays a role. So it'd be useful to annotate that. And again, we're mainly 2 players are involved in a penalty. So we're going to have 2 players annotated in this data set. Okay, it's not yet publicly available, but we're working on it. There's some legal issues, but with the university, they want to make sure that we have rights to submit this and work with the NHL because the source is from the NHL broadcast. But hopefully, this will be made publicly available soon. Okay, so here's some examples. The first one at the top is an example of the hooking. Okay, so actually, the person's not using a stick to do the tripping here, actually using their leg, which is another way to trip people, more like you see in soccer, I guess. You can do tripping in soccer by sticking your leg up. And the one in the middle is a slashing penalty. That's whacking the other player's sticks or mainly their wrists, so forth. And then the last one is a non-penalty situation. It's actually a face-off, okay, which may look somewhat like slashing, because people's sticks are whacking each other. Okay, so these are just examples of the three classes, and these are video frames that we have. Okay, now, since we're basing our approach on pose information, so the joint information, sort of the quality of the pose estimations is important. Okay, so we investigated, different methods for doing pose, and so the two main ones we're looking at is this associative embedding approach, which is sort of bottom-up approach, contextual instance decoupling, the top-down approach. So these are, methods that are available in the literature. We don't include the hockey stick pose because typically these pose estimators don't know about hockeys, so they don't provide hockey stick annotations. And we're going to use these for later results, but this is just looking at the quality of these pose estimators. Now, the first line says pre-train only is basically taking one of these methods to train on whatever data set and applying it to our hockey data set. Okay, and here's the typical measures, average precision and so forth. But then we also fine tune these on our hockey set. Okay, so we take out a part of the training set to sort of fine tune these pose estimators. You can see that fine tuning actually helps quite a bit. Okay, to fine tune these pose estimators on the hockey data set. Okay, we get a fair bit of improvement on the pose estimation, but it's still not perfect. Okay, but it's what we can work with. Okay, and here's some examples, just the influence of doing fine tuning. Okay, on the left is the approach provided, without the fine tuning, and the one on the right is with fine tuning. You can sort of see in the upper left, the goalie is not basically the pose is not available at all. But if we fine tune it, we can actually get some reasonable estimations. Okay, so this is our input. Okay, and here's some results on applying our method to this penalty classification application. Okay, and this is using either the ground truth pose. So in our data set, we did hand annotation, and the other authors in the that are listed at the beginning, there were undergraduate students who actually did a lot of the labeling and annotation, as well as some of the coding. Okay, so we have ground truth pose, okay, compared to using estimated pose. Okay, we can see that these are the first three rows are other types of methods. Okay, work better or worse. And then we have in this row here, ARNW without these relational features, this added information, we get fairly good results, 91. But if we add now these features, we get an increase of about 3%, which improves things quite a bit. So just showing the importance of these features. Now, this is with the ground truth pose, okay, from our hand labeling. If we use the estimated pose, from the approaches that we just talked about before, okay, the results are not quite as good. Okay, we drop about 7%. Okay, sort of indicates sort of more realistically what we get with sort of automatic pose estimation. Now, we can apply this method also for other data sets. So we showed the results on hockey, but we can show results on other data sets such as SGU and NTU. I just want to point out a couple of things. So saying the left-hand one, which is looking at SGU data set, we compare it to a number of different approaches. IG form is a transformer-based approach, which is rather computationally expensive and large. Then we have an LSTM-based model, okay? And we say that our method is competitive with the larger models, the transformer-based one and the LSTM-based one. And the same holds on the NTU data set. And you can see here, we've actually indicated the size in terms of number of parameters. The IG former, like I said, it's a transformer-based approach. That's about 20 million parameters, whereas our network, full network, is about 3.5 million parameters. Okay, so it's about a seventh amount of computation, but it's getting comparable results on these data sets. Okay, so in conclusion, just some takeaways, we did a number of ablation studies as well, just to give you some idea of different aspects of this. So the object structure matters, okay, how you form these objects and what sort of features are available. And also these relative features, which we added to these just to joint information, are very informative. They actually do make a difference. And also it allows us to basically get temporal information embedded in our system without using recurrent networks such as LSTMs or transformers. The parametric aggregation over non-parametric both this scale dot product over sort of additive tension actually improves things. We don't show the differences here, but this attentional focus of which sort of relations are most important actually improves things a bit. The pose quality makes a big effect here. We have to have good pose. If we don't, then the method drops. But that's the same for basically any pose-based action classification approach. The method is very simple. It's competitive with these more complex methods such as IG forming. I'll just point out that the hockey penalty database is actually fairly challenging for sort of state-of-the-art pose estimators because there's sort of strange poses that the hockey players get into. They're lying on the ice or the goalies are all punched down and have a strange shape to them. Okay, so thank you for your attention, and for more details, should send Faye an email. We'd be happy to hear from you.
Thank you very much, James, for the great talk. So we are running a bit late, so we've got time for one question.
We could do it. Yeah.
Very nice presentation. One question, you mentioned that the body pose features of the interacting players. I assume that the two opposite players from the change that they So how the model works if you, for example, every pair of the players that are interacting or everything that change rather than just knowing that who are those interacting players.
Right. So that's a very important point, because when we did the manual automation annotation, of course, the human annotators decided who were the main actors. Okay, so we can approach this in a number of ways. One is to do basically key actor detection. Your colleague Siavas has worked on with our group, which is challenging in itself. Okay, it can be done. Okay, and there are methods for doing that. And for this accident, they worked fairly well. But sometimes it's hard to determine who are the key actors sometimes, especially when you have a long video, because sometimes it only becomes clear after a little while who the key actors are. But the other approach is what you alluded to, is we can actually extend our representation to, like where we had two people, we could extend it to 3 and 4. Okay, and we found that actually works very well. It reduces accuracy a little bit. Okay, because now sometimes we get the wrong interactions, but we can do that. That adds a bit to the computational complexity. Now we have more features vector, although the complexity grows fairly slowly. Okay, as opposed to say a graph convolutional network where we have to add more nodes. Okay, then it sort of blows up. So we have done that. We don't show the information because our data set is sort of has it annotated, but you're correct. We could do also, you mentioned we could just do pairwise of all the different people. I don't think that works as well as extending the number of skeletons we have in each object. That's probably a better way to do it rather than doing pairwise, which increases the number of features quadratically. But that's a good point. Okay, I think doing key actor detection maybe is the best way, but that's a separate problem.
All right, let's thank our speaker again. So we'll have a bit shorter coffee break than anticipated, but feel free to go get some coffee, something to eat, maybe upstairs. I think around the poster area, there should be stuff. And let's get back here at 10:45 for first a keynote talk by David Zambrano from Sportradar, and then 3 interesting oral presentations. See you. Hi, how are you? Meet you. Nice to meet you. How are you? Yeah, great. Looking forward to your talk afternoon. Yeah.
Yes.
How are you?
From Jens Group, right? I know personally Jens. I have worked with him when I was in Cows.
You are so much busy, you are not giving us time.
Yes, oh, I know. It's a busy time right now.
Just a technical question.
How's everything?
Yes. Yeah, good. Yeah. I have seen since you look at me at the beginning, I was looking at me, he was looking at me, but we never met. So we were, maybe yes, maybe I was sure, okay, it's okay. Saying hi. Perfect. And yeah, thank you so much for sponsoring also the workshop. As our fitness. I hope that yeah, I hope that it's just exactly. That's the point. Oh, you got your T-shirt. Yeah, one for me, one for them. Yeah, that's perfect. Take some for your team as well. So I'm gonna grab some conference. Hey, yeah, I met you already. I think. Yeah, but we have many interesting. I see your name a lot. Really great. This year was really fun. Hopefully next year we get to join that. Yeah. It's like can't find it. We just one like so here you from the MV right? Because I remember your name, but I just want to make sure I'm right. Why not just extend it? Yeah. Oh, have you registered the social event? Okay. Yeah, you will be able to. Let's discuss with them if they are utilizing data, because this is also what we experience, is that it's very difficult to get data on your access. Because the teams don't want to share that. So we got partners from Qatar Foundation. So, yeah. I'm not sure as it was Silvio was and so yeah, as a foundation, and then we have also television in France, or capture data and that with us. Yeah, and these are and one from the Swiss League from another partner in Europe. Because they are interested actually in seeing what the other side to with the
Yeah.
Their incentive to say, okay, there's the potential so we don't pay them, we just share with them.
Oh, yeah, it's just.
But with limited access, it's just research. People
Yeah.
using IEEE.
Yeah.
So it's like all we are doing is sharing this research. It's very useful.
Yeah, that'll be nice. But I'm not sure.
The annotation we did.
I did myself.
You did yourself. No, we did that the first week of SoccerNet. So we see your students like I'm consuming. We have 800 hours. Yeah, imagine. So yeah, it's like so we have funding from either Belgium and Europe from partners. And we really need for what we do for the challenges, we really need manual implementation. Because otherwise you're just comparing. That's that makes sense.
I was there doing master's.
We really need the
It's a bit of
manually implemented annotation.
When you completed your masters and now the PhD.
Yes, yeah, so we did for action spotting, for instance, there were also just for round one, and then give it to the yeah, all by ourselves. And then we hired 30 students from the university. Yes, and to annotate manual. Yeah, all we do is manual annotation because we want high quality annotation. So we don't want semi-automated stuff. It's just, I think the only thing we did semi-automated was for tracking the bounding boxes. We did the full one and then that. Yeah, there's the rest is all. But it costs a lot. I think we poured hundreds or thousands of dollars into it. But in research, we can get the money from like federations, institutions. It's not like making a product for that's something really more need to pay. Yeah, like dancing match. Yeah, it's really nice. Looking forward to later and faster. Yes.
Yeah, that's all. But you do like. Yeah, small steps. Oh, yeah. No, like what again? So, depends on a lot of luck as well. Yeah. Are you training This has been like 100 people.
Because I saw there was a paper so it's actually five. Yeah, because there's multiple there. I see and I think sports there was deep sport radar challenge, right? Are you going to take another day? That's the only thing I can share. Everybody gets stuff secret. You have not played anything. Know what we get. Nah, yeah, bring stuff but monthly there's challenges yeah, we always say that. Sports. They play sports and because anything in place, there is yeah, so actually, I mean, I know that what should be really cool to do, but not really to the impact of the average one. No, that's a judge that. Few titles with Steve from university. I really appreciate organizing that challenge. Yeah, very interesting. And a bit of a hard time. Finding people together who are very interested in things like in science. Yeah, it's like here. The patient, I see it. Years ago. Yeah, we don't say make. Yeah, we can also.
I have a question. How much time have you spent buying boxes for the annotations for data?
Yeah, so we 12 towards the I get ready for 2 months. This was with basically we spent €20,000.
Okay.
It's exactly. But I don't know how many people work on it for talks. Maybe 10, maybe 20. I don't know.
Are you going to continue expanding or?
Yeah, we're looking the issue that now the addition of the do costs really a lot. Like the line also cost a lot of things that we have to strategy. And then we want to do first trial, but this is going to be more expensive. Yeah, and we relatively much say that everything. Yeah, and then maybe make campaigns for a treat, but we don't want to view. But this is really like yes. I really protective of that. Something all about values that to be
Maybe like lessen the level of the team. Is that something that you want to keep at a high standard? What we did, we were working with university teams, and they're quite forward and positive in working in revealing data. They're not as strict protecting their videos.
Yeah.
High standard.
Yeah, no, I mean, this is fine. Amateurs games are also having the data available. That's what I mean.
Nice to meet you.
Nice to meet you. Attitude. University of Ghent.
Yes, I saw your name as well.
Let's after a little.
You might want to start because all right, let's start back. So thank you for still being here. I'm sorry that the break was a bit short. We'll try to stick in time right now. We have an exciting program until noon. We're going to start actually with Davide Zambrano here, who's a lead deep learning
Tech lead
researcher in Sport Radar. Sport Radar is also a sponsor of our SoccerNet challenges and have been a collaborators for many years. So I'm really happy to welcome Davide here to present the latest research and the interesting topics that Sport Radar is working on.
All right, thanks. It's a very pleasure for me to be here, and I'm honored. Today I'm going to talk about the relationship between data and metrics, at least from our point of view. And the title here, as you might guess, has been generated by ChatGPT. I thought it was interesting for the topic. All right, so I will start with who we are, what we do, and our motivation. So Sport Radar is at the intersection of different sports, media, and betting industries. The core business is still betting, which means that we make the odds. But the company is more and more opening toward computer vision problems. And with its partnership with the NHL, NASCAR, UEFA, FIFA, ICL, IGF, tennis, so many federations, organizations. We are like the computer vision team. We call ourselves automatic contents. And we analyze sport events such as basketball, tennis, table tennis, esports, and other sports that are coming. You might have seen the video on the left side showing all the things that we can detect, for example, from a tennis match, and eventually augment the streaming with this kind of information. About me, something I was former PhD in biorobotics and former researcher in computational science, reinforcement learning, spiking neural networks, all sorts of things. Now I've been on computer vision in the last 3 years with Sport Radar, and my main focus is player tracking in basketball, specifically for the Division I of the American colleges, NCAA. Now, in our domain, it's important to keep in contact with academic research because this is where we get the most information, most useful information, and we want to engage the scientific community. We want to explain who we are and what we do. We want to push the limit of the state of the art. So we want to understand what are the technologies that will help us improving our technology. We want to grow our potential in terms of things that we can do inside the company, and eventually attract also engineers in our team, so why not? We do that through our different means. We have PhD students collaborating with us and funded by us. We have master thesis, internships, scientific publications sometimes. But one other thing that we can do is to provide data, because at the end, we are a huge collector of data, and we can give something back to the academic community, and in the form of data, in a way, we drive the research toward data that we have and toward the problems that we have. And so we did that toward the very prior event, which is another workshop in ACCB for data efficiency. SoccerNet is another example. We collaborate, but we also organized our own challenges. We call them Sport Radar in the last couple of years, 2022 and 2023. So we have computer vision challenges, and I'm going to talk about them today. So we mainly organize 5 computer vision challenges so far, 4 in basketball and 1 in cricket. Player instance segmentation, re-identification, camera calibration, ball 3D localization. And in cricket, ball release detection, which is a sort of action detection in cricket videos. So for each one of these challenge, there is a GitHub page where you can obtain data, read the annotations, consume the data, and use the metrics that we proposed in the challenges. And there is also baseline of code that shows how to consume the data properly, and eventually could serve as a starting point to make different models on them. The first one, ball 3D localization, is interesting because it wasn't very popular. And the idea is we want, actually, this is something that we do in our company. We're trying to localize the basketball ball in 3D. And we do that here by estimating the diameter of the ball, because the ball has a fixed size in reality. And so if you have projection matrices, you can actually determine the localization of the ball. So this is not an easy problem. This is one way to solve it. We define a metric for it. We design the data set. We provide data set annotations in 3D, but we also define the metrics that should be solved. Wasn't very popular, but at least the solution was improving our baseline. Another one was camera calibration or camera registration for sport fields. Here we provided 700 images that split in different sets. The interesting part here is that these views are automatically generated. So you can actually regenerate a lot of views from different point of views. And these views, they contain their own projection metrics. And so by this, you can generate like an infinite amount of data for a basketball field. The idea here is to register the field, so to know the projection matrices by detecting first the lines, the court lines, eventually with a segmentation model or whatever. And out of these segmentation points, you can make this matching between the 3D localization of the court points and the image points that you detect. And so this will allow you to predict the projection metrics. Of course, that's what we wanted people to do. We got a couple of submissions, but the interesting part is that the winners were actually posing the problem differently. So first of all, they spotted that our evaluation metrics was actually only considering point on the ground. And so this allowed them to predict not only the projection metrics, but only the homography, which is a simpler problem. And they also applied a variation of this work published by IEEE in 2021, with a few variations that are specific to our setting, in which, for example, since the camera is always placed on the left, on one side of the court, the ground points that you see the pointer that you see here, if they are displays in a more in orientation that mimics your point of view, you will have a better distribution of the points. And so this improve their performance. Instance segmentation is actually a problem that is a little bit more important and let's say popular in computer vision. We have images, more than 300 images, with 2,500 high quality instances. Now, instances are not very common in public data sets. So this was very well received. It's also interesting because basketball provides you a lot of occlusions to work with. It's also a single class. So you don't have to scale the different results based on the different sizes of the object that you are trying to segment. And you have a lot of contrast, like not very good contrast with background, so it's not an easy problem to solve. We started in 2022 with standard metrics for segmentation, so measuring the mean average precision. But we saw that on the left you have the results of the first year, and the participants kind of saturated the data set. And so we, in the second year iteration, we proposed a different metrics to let them focus specifically on the occlusion problem. And so we, the metric that we introduced really tries to focus on the part of this segmented object that is disconnected from the main, and the ability of the model to say that this is still in the same instance. And this was actually better to distinguish the different approaches and to find something that was useful, at least for us, for our proposals. So again, this is a tight interpretation of how data and metrics would really shape the research that is done. This is the proposed overview, proposed solution overview. The participants trying to solve this by using hybrid task cascade network, which is popular in that specific in this specific context. But the specific problem of the occlusion, they try to solve it by placing masks, augmenting the images by placing masks on different locations, which is not an easy task. That's why they had to with core detection and playable area selections, and then in order to pass the objects on top of the image. And this kind of augmentation improved their results. So again, the research is specifically done in order to improve on the metrics that we selected for that. Player identification is another popular task in computer vision. Here we speak about recognizing one player among a gallery of others, thumbnails, and the idea here, we took this data set from sequences, sort of a video with a higher, lower sampling rate, about 100 milliseconds from image to image. So the idea here is that we sampled those frames, we crop the images, and we have identities of those players. We use the first frame as a query, and all the other frames, even the other sequences, as a gallery. And we need to re-rank them. And so to try to define, to find the same player over your gallery. This is posed as any re-identification problem. And unfortunately, again, the results were kind of saturating our data set, having most of the participants reaching very high scores quite easily. We got a very interesting approach here that I wanted to mention. They used clip so clip, it goes from text to image and image to text. And they only use the encoder, the image encoder of clip, and they use two encoders in a sort of Siamese network to train a model that re-identifies the player from the query to the gallery. This approach was actually very interesting and very innovative, and so that's why I decided to mention it. We retried in the 2023 with a second edition of the re-identification challenge. This time we introduced more images in the gallery set in order to complicate the things for the participants without being very successful at it. So the participants were actually able, all of them, to reach very high scores in MIP. And the interesting part is that at the end, they use the same approach of the previous year, the winner of the previous year, since the code is available, and they try some improvements here and there from some augmentations to just improve the results on the final challenge set. The last challenge I wanted to describe is the cricket ball release. So cricket is a very long game. In the let's say in the original formation, cricket could last even days, right? And it's important, it's imperative to define where are the important things in cricket. So where are, for example, the bowler, which is the guy that is like running now and launching the ball, is doing the action. So these are important things in this game that we want to detect. So we treated this as a kind of time segmentation problem. And we define a metric specifically for it, which resembles the panoptic quality in instance segmentation, but for the time. So, for example, if you have on the here, you have the ground truth, and then you predict that the bowling event is all the frames that belong to this gray area, then you can eventually make matches. Like you can match and say if the bowling event is at the same time of the ground truth, but you also have false positive and false negatives. And so the panoptical quality actually is a multiplication between two parts. The recognition quality takes an account how many false positive and false negative you have. And the segmentation quality takes in account how good you are in matching exactly the frames in the ground truth. This was actually, I think, pretty well designed metric for the task. However, the results weren't very satisfactory in the sense that probably they will have required a little bit more time to with the data in order to have high quality of like high scores in the PQ. Anyway, so those are all the challenges that we proposed, and I want to go now into how these become something useful for us. What we do is player tracking for basketball, and we start from this, which is a product that we have installed in venues, for example, in American colleges, and this product is based on 3 cameras that look at different parts of the court. Then since the cameras are calibrated, we can stitch together all the images and have one single panoramic view. We can detect the players, understand where the action is, and create these virtual views, which are basically the same view that you would get by a manual director, like looking at the game and broadcasting the game. And so this is what actually you will get out of the system. So this is the image that we consider our input. So what we do is then we take this image, we know the projection metrics, and we do all those computer vision tasks in order to track the player on the ground. And these are some results I can show. Of course, I cannot disclose a lot of details in terms of the architecture and what they use. But what I wanted to say is that here we are able to create this product thanks to the combination of multiple computer vision models. So here, my point is, out of those computer vision tasks, this is not one single product that you are selling. You're selling a combination of them. And it's important that you collect enough data for each one of them, and that you measure the performance of each one of them in order to get a full picture like this. I have other few examples to show about our results, actually even not good ones, as this is for FIBA course, which are slightly different. We can reproject the court lines. We can reproject the players on the ground and pace them in order to show the motion. We can detect the jersey numbers, the jersey color in order to clusterize them in different teams. All of that to track the players and understand who did what. And this is just one part of the full product that will be served for American basketball colleges. So evaluating our system is not an easy task. So we can evaluate each part, but we also need to evaluate the full picture. And tracking, of course, has a lot of metrics around, but you also want to understand exactly what you do with a more direct way. And here we propose something that is very similar to the this year competition, soccer competition metrics for the holistic task, I guess it's called. So what we do is that we try to match the ground truth with the annotation, with the predictions. And from that, we can get false positive and false negatives. But we also can detect which kind of errors we make, for example, for the team affiliation, as in the bottom left, or for the jersey number recognition, which is a different number. And then we can get the rate out of those detections. What I want to say is that this is what we use to drive our research. So no matter if one model gets much better results in their own metric for their own computer vision task, what you want is to try to finalize everything in one single number that drives what your stakeholders need. As a conclusion, so we know that deep learning and computer vision is important for sports analytics. They play a crucial role, but they come with the prerequisite of acquiring a lot of data and precise annotations, which is not easy task to do. We propose challenges in order to drive the community toward our task, to enhance ideas toward our problems. These are free for everybody to use, and we hope that we can engage on this future. The main conclusion we got from these challenges over these years is that, first of all, every sport is different. It presents its own challenges. You need to have experts or an expert point of view to detect exactly the important part of the game, the dynamics. And so it's not that one object detector that you train on Coco will necessarily work for basketball or for soccer. Everything is different, and you need to understand that from the different model perspective. And the second thing is that the metrics themselves that you design, they really drive your research, your approach. It's important to measure everything that you do in this kind of task, but also to stay close to the final product. So stay close to what your customers need in order to measure what you're doing, when your product works and when it doesn't. Thank you.
Thank you, Davide, for the great talk. Do we have questions in the room? Let's start with Nitish.
Hey, really great work on player tracking. And I'm really impressed by the fact that you've also released the challenges and the data sets. My question for player tracking is, how do you deal with like occlusion, especially for jersey number identification? And secondly, how do you stitch these, these boxes that you were showing for different cameras across frames and especially across different cameras?
All right. So for the first part, I cannot say much. I don't really, they told me not to. But let's say that you can build a sort of representation of a player over multiple frames and eventually correct for that. Maybe in one single frame, you are allowed to make errors, but over a bunch of them, you can recorrect and decide which prediction is more likely to be true. That's all I can say. On the second question, here there are two different products. One is the one that produces the stream, right? This view of the basketball game. But we consider that as an input. So basically, we don't have access to the 3 cameras and the stitching problem. We only have access to the frame view, which is this one. So this is it's a matter of these 3 cameras are installed in the venues, and it's not easy to stream all of those for later quarters. So the only data that we actually can work on is the this frame view. So I don't know if this answers your question, but we don't have to consider the different cameras in our problem. Our problem is only tracking from this point of view.
And the final result, final result of interest is the position on the ground where the players are from this one camera.
Yeah, because the view that they provide us contains the projection metrics of that specific view. So we can, for example, if here I'm highlighting, re-rendering the middle point of the bounding box, okay, you can use others. Doesn't have to be that one. You can even be a bit more accurate by using the projection of the center of mass. But let's say that for our first approximation, you can use the middle point of the lower edge of the bounding box and reproject that point on the ground because we have the projection metrics. And those are the points that you see here in the minimap view.
Perfect. That answers your question. There is a question on the back here. Yeah.
Is the system you're showing us, is it completely automatic, or is there any?
Completely automatic.
There's another question here, Victor.
Yeah, you mentioned that you had a lot of trouble designing a good data sets. And in hindsight, what would you say is the most important thing or the biggest thing that makes the data set work or not work?
That's a good question. So I think the quality of the annotation is important, and the fact that you can Q&A them, like whenever you find inconsistencies, you can go back and adjust them. That's one part. Quality of annotation. I think quality of the annotation and the dataset is imperative. I would say that you want to be broad as much as possible because you want to work well on different scenarios, and that's not an easy task to do. So it's even for the annotators, from the annotation point of view, it's not easy sometimes to understand who is the player, where the player is, and what's the jersey number or something. So, but this definitely helps the model to generalize over different venues and different location of the camera or different situation of different jersey color. Sometimes these players, I mean, in NBA this doesn't happen, but if you lower the tiers of the divisions, you might have jerseys with like blue jerseys and the blue jersey number printed on top of it. Like there is, even for a human eye, from that point of view, it's impossible to understand which number it is. And not surprisingly, we are not performing well on those.
Any other questions in the room? Yeah.
I'm curious how directly applicable you found the outcome of the challenges that you published to your actual work, like or productizing. Like, do you find the models that end up being able to maximize the metrics that you've got feasible to release to production and so forth, or do you take them as a guide, or how does that work?
No, absolutely no. At the end, it's more an inspiration for us. Like it's very hard to understand. I think this is kind of question that I keep asking at every director or whatever in companies. The amount of research that you have in your company with respect to putting things in production, right? Engineering versus research. And in our case, we kind of had the opportunity to spread a little bit more the voice because we could get some ideas out of them. Maybe they are not directly related to our product, but at least we get some interest, and these are material for thoughts. But if I have to say that any of those approaches were particularly successful for our products,
that's not the case. Any other questions in the room? Last question, maybe.
Also, another question. Have you consider tracking identification? I mean, the results you're showing here look like really impressive. Would you consider that a solved problem then?
Absolutely not.
Then, like, is this just like a good example, or what are
Yeah, I think
remaining challenges?
so without entering into details, I think we make on this rate that I showed before, we make on average 6% of errors still, and our stakeholders are still expecting us to go to 0, which I find impossible. But definitely our intention is to get a lot better, especially in venues where we have difficult point of views and maybe resolve them first. So in the examples I've shown, 2 of them are good, but I think this one, there are errors. They're difficult to detect, but there are errors in identity switches and things. And the problem of occlusions still arises. And when you can't see where the player goes, who the player is, and because in the key errors, like around the net, a lot of things have happened. It's a very difficult problem from one single point of view. If you only have one point of view, it's very difficult to eventually resolve everything. I guess we will try to improve over that direction. There are many other things we can try, and being here for me is another way to learn new ideas, but it's not definitely a solved problem.
Okay. Any other questions in the room? I think maybe for interest of time, we're going to go to the next speaker. Thanks again, Davide, for your presentations. Great insight. All right. The next session, it will be 3 oral presentations of papers that has been published at CV Sports. And our next presenter is Takuya Nakabayashi.
Yeah.
Good. With a paper called Event-Based Ball Spin Estimation in Sports.
Okay. Hello everyone.
Test. Is anyone logged in on Zoom or something?
Presentation. of spin speed is limited by
desktop. Test.
Sorry, the first limitation is estimable range of spin speed is limited by a shutter speed of a camera. And second is moving or spinning balls are often broad and makes it difficult to estimate the spin accurately. We use event cameras to overcome the limitations of frame-based methods. Event cameras output the brightness change as events. Events contains 4 pieces information: X coordinates, Y coordinates, timestamp, and polarity. X and Y coordinates indicate where the brightness change on the image plane, and the timestamp indicates when the brightness change. And the polarity is a binary data indicating whether the pixel gets brighter or darker. In the context of sports analysis, the term events commonly means sorts of activity in sports matches. But in this presentation, events means the information of brightness change. So be careful to not to confuse them. Event cameras have several advantages over conventional frame cameras, such as high temporal resolution and high dynamic range. These features overcome the aforementioned challenge of frame-based methods. In our work, we apply contrast maximization to both spin estimation. Contrast maximization is the algorithm to estimate the motion parameter from events. For example, a black square moves from top left to bottom right with uniform linear motion, and I'll explain how to estimate its velocity from events using contrast maximization. In general, most of events occur around the edge of the object, spatially. So events are aligned based on its motion trajectory. This bottom left videos is a visualization result of events in XYT space. And it shows the position of events aligned along the motion of a black square. Now consider working events with uniform linear motion at a specific velocity. If we warp events to the specific plane in XYT space with correct motion parameter, the warped positions are overlapped because they are aligned along the trajectory. And then the contrast of IEEE is maximized. IEEE is the image whose pixel values is the number of warped events. On the other hand, if we work with wrong motion parameter, the contrast of IEEE becomes lower. Consequently, we can estimate the motion parameter by updating the motion parameters to maximize the contrast of IEEE. The process of spin estimation in our method is almost same as this example, but in this example, we assume the uniform linear motion, not the spin. So in our work, this warping function is different from this example. Okay, so I'll explain how to estimate the spin in our approach. Our approach takes the event stream and the manually annotated bounding box of the ball as input, and outputs the 3D axis, 3D spin axis vector, angular velocity, and translational velocity on the image frame. First, we project all events to 3D space because we want to estimate 3D spin in the 3D space. Since events are generated by the motion of the texture on the ball, so it is possible to compute the 3D position of the events if the ball is assumed to be a perfect sphere. Using the information from the bounding box of the ball, the depth corresponding to each event can be computed as shown. And second, we compute warp position of each event in 3D space and create RWE based on it. And then the motion parameters are iteratively updated to maximize the contrast of RWE. This bottom right video shows the contrast of RWE is maximized as the iteration goes. Okay, so next I'll explain the experimental settings. We use two data sets to validate the performance of our method. One is a synthetic data set, which is generated with Blender and event camera simulator. And the other is the real-world data set, which is taken at an actual variable match. Also, we implement frame-based method as a comparison method. This is based on the work by Tamaki et al., and it takes adjacent RGB frames as input and estimates the spin. This is a result on the synthetic data set. These two graphs show the estimation errors of angular velocity and spin axis vector. In both graphs, the orange line shows the error of hours, and the other line shows the that of frame-based method. As you can see, the faster the ball spins, the larger the error in frame-based method becomes. On the other hand, the error in our method remains small even when the ball spins at high speed. This result indicates the effectiveness of event cameras in ball spin estimation. And next, this is the result on the real-world data set. RGB frames are severely blurred, and it should be difficult to estimate ball spin from them. The video on the right side is the visualization result of spin estimated with our method. It can be said that estimation results are reasonable by comparing the motion of texture on the ball with estimated spin. As you can see, our approach can estimate various spins accurately. And these results ensure that our method works on the real-world data too. Okay, so let me conclude my presentation. In our work, we use event cameras to estimate ball spin. The high temporal resolution of event cameras enables us to estimate fast ball spin, which is difficult to estimate with frame-based method. Okay, that's all. Thank you.
Thank you for these great presentations. Is there any question in the room? There's one here. Let's start here.
Yeah, any idea how well the back cameras work in, say, a high contrast environment? So like an open baseball stadium where half of it is in shade. So if you have a large amount of sun on the top of the baseball, and then it will make it pass into a shady.
Well, yeah, sorry,
let me sort of answer, because I was
Okay. Probably even in the outside.
Hmm.
We believe that event camera can capture something, because event camera will capture only the difference, intensity. That's why, we didn't try yet, but, we believe that even in the outside, so they, sort of, sunshine and something.
Yeah.
We can do this probably. So maybe, yeah, some other people who is working with the event camera might be able to answer. If a very large range, so they were people can share that.
Yeah, maybe I'm not sure to understand how would you use event cameras in a real context in which, because as far as I know, they have very poor relative resolution, like not many pixels, which are not really pixels. And so if now you're focusing on one details, which in a large image, it's like a crop, like
Yeah.
a single detail, but how many cameras would you need to detect the ball spin during a match?
I'm not sure, but yeah, the resolution of event cameras is low for now, but yeah, so yeah, many event cameras is required to for for um for court.
In this case, how many pixels
Sorry, the resolution of event cameras is 1280 by 720.
In this case, how much resolution to be required to get the ball spin? In this case, in this particular case, how do you expect that, how large?
Yeah, in this example, the size of the ball is about yeah, 100 100 pixels by 100 pixels. Yeah, but even when more small ball, our method can work, maybe.
Thank you for your comments. We need to focus on the how much size can be, so we didn't try sort of extreme case. We also capture the wide angle situation for the variable match, last January. So we also try to
So you acquired the data set yourself?
Yeah, we want to publish the data set future. So that is actual professional match, baseball, variable league in Japan. So
the camera was fixed.
So we fixed the camera. So we placed the cameras in the studio stadium. So we brought the cameras. Thank you.
All right. Sorry, for the interest of time, I think it would be better if we can take those questions offline. I know there's a lot of people working in event cameras. I would definitely recommend to contact the authors. But just for interest of time, I think we need to go to the next speaker. Thank you. Thank you. Thanks for the question. So our next speaker is Jan Held. Jan Held is gonna present us a paper called XVARs, Introducing Explainability in Football Refereeing with Multimodal Large Language Models. Perfect. Jan, the floor is yours. Yeah, not. Yes. Great. Perfect. Very good. Floor is yours. Hello, everyone, and welcome to my presentation of our paper called XVAS, introducing explainability in football refereeing with multimodal large language models. This project is a collaboration between the University of Liège from Belgium and KAUS from Saudi Arabia. The life of a football referee, it's not always easy. In each game, I always take a decision where there's one team who's not happy at all. In those moments, the coach, the players, and especially the spectators are all shouting at me. As you can see here in two examples of 2 FI games. In those moments, you have to somehow convince them that the decision that you took is actually the correct decision. But how can you convince them? You have to explain them your decision. You have to explain them the reasoning behind your decision. You have to explain them the laws of the game and the rules of the game. Then most of the time, you're able to convince them. That's exactly the research question that we asked ourselves for this project. Can we use large language models to generate explanations that can convince experts in their domain? And I think football is the perfect playing field for this research. A decision a referee has to take is a lot of time very subjective. If I would show you a video of a foul, there would probably be a lot of people who would say, oh, that's easy, that's a yellow card. Some of you would maybe say, oh, no, it's a red card. Maybe one or two would even say it's not a foul at all. I think that's exactly what we wanted for this research. Can we build an AI that can take decisions and explain its decision in such a way that it can convince referees? And therefore, we introduced explainability. And the idea was very simple. We give as input to our model a video clip of a potential foul and a question. For example, was it a foul or not, and why? And what we want is that our model can now output its decision. For example, it's a foul and a yellow card, and also an explanation which explains why our model thinks that this decision is the correct decision. But how can we train such a model? The first step was to build a dataset. So we built the SoccerNet X-Foul dataset, which was obtained during an annotation campaign for over 3 months, where more than 70 referees annotated our data. At the end, we obtained more than 22,000 video question answer transcripts. As the decisions and explanations are very subjective, for each video and question, we do not want a single explanation, but multiple explanations for multiple referees. Next step was to build the architecture of our XVAS. The main foundation of our model was obviously a large language model, where we give as input a user input, which is the question that we want to ask. Then we also have to somehow input the video information. Here we used a pre-trained clip model, where we push each frame of our video through clip to get spatial information of each frame. Because the temporal information are also very important, because the speed, for example, of the tackle is very important to take your decision, we mean aggregated the feature along the temporal dimension to also get temporal features. So at the end, we have spatial temporal features. The next step was to push them through a linear layer to project our spatial temporal features in the same dimension space as the text embeddings of our language model. Then finally, we obtained those video tokens, which contains the information of the video. Next step was to take the spatial temporal information of features and push them to 2 classification heads. The first classification head makes a prediction of one of 8 classes, which represents the type of foul. For example, a tackle, or pushing someone, holding someone, or for example, if the attacker makes a dive, if he wants to deceive the referee. The second classification head makes the prediction of if it's a foul or not and the severity. So it predicts no foul, foul and no card, foul and yellow card, or foul and red card. And those 2 text predictions are also inputted to the model. So we give the user input the question, the video tokens, the video information, and the text prediction. And our language model now produces an output, which is then the decision and the explanation. To train our model, we first had to fine-tune clip, because clip was never really trained on football data. So we had to inject some football knowledge. So we just fine-tuned clip and our 2 classification heads. For the second fine-tuning stage, we just freeze clip and our 2 classification head, and we just fine-tune this linear layer to correctly project our spatial temporal features in the dimension space of the text embedding. The large language model that we use is Llama, so we use the pre-trained weights, and we just fine-tuned 1% of the layers. Now it's the interesting part. Let's have a look at some results. Let's see what the decision and explanation of X bosses. So it says, yes, it is a foul. The defender is holding onto the arms, the attacker's arms. Now, for this dangerous tackle, X boss says the defender's tackle was done with moderate intensity while he attempted to play the ball. However, the speed of the tackle and the direction of his feet show a lack of consideration for the well-being of his opponent, and therefore such an action should be considered reckless. The player should be punished with a yellow card. You can see that now the model does not only take a decision, but it really explains why he thinks that this decision is the correct decision. And the explanations are also very in alignment with what actually happens in the video. Then we also went a step further, and we wanted that you can not only ask a single question to our model, but really have a conversation. You know, there's a little bit of sound, but anyway, so here, if we ask, is it a foul or not, and why, X bar says, yes, it is a foul. The defender hits the attacker on the foot. Did the defender play the ball? No, the defender did not play the ball. The attacker was trying to play the ball, but the defender hit him on the foot. Now we can really have a nice conversation about the video clips from the point of view of a referee. Now the next question is, how good are the decisions that our X-VARs takes? So here we did a human study where we compared X-VARs to human players and to human referees. So we showed to 15 referees and 15 football players 20 videos. For each video, they had to take the decision no foul, foul and no card, foul and yellow card, or foul and red card. So they had 4 different possibilities. If they would take the decision just by random, they would have an accuracy of 25%. The football referee got a score from 45%. VAS, which we presented last year here at CV Sport, got a score of 51%. Players got an accuracy of 58%, while our ex-VAS got 59%, and human referee 60%. So we can see that we're actually very close to human referee performance, a little bit behind, but still on a very good way. The next thing we had to check was how good are the explanations that we generate. So here we had to perform a second human study where we asked 20 football referees and we showed them 20 videos. And we gave them a question and, as you can see here, explanation. But they had no idea if this explanation was now generated by our ex-VARs or by human referees. Then they had to score it from 1 to 5, where 1 is I strongly disagree with the explanation, and 5 is I strongly agree with the explanation. At the end, the explanation of the human referees got a score of 4, which basically means that in average, the human participants agreed with the explanations of the referee. While our ex-VARs got a score from 3.8, which is again a little bit behind human referees, but still very close. Also, if you have a look at the distribution of how often each score was chosen, you can see that's very similar, and that ex-VARs and referees have or in average, the percentage for each score is very similar. You maybe just have a very little difference for the number of disagrees. So ex-VARs got maybe a little higher percentage of disagree scores, but overall the distribution is very close. In summary, I think large language model can really be used in the future to support or offer explanation in classification problems, not only in football, but it can also be very useful in other domains where, as a human, you have to trust the decision of an AI model. I think that ex-VARs already has a very close performance to humans' performance, and in the future, it can definitely support referee. However, also our work does not come without limitations. For example, one big limitation is that the input that we give are just 5 seconds video. But if you want to give maybe 30-second video or maybe even a minute, 2 minutes, that's definitely something we have to improve in the future. Also, our data set is quite small. I think we have, for example, we just have, I think, 25 red cards in our data set. So for an AI, it's quite difficult to really understand the difference between a red card and a yellow card. And finally, evaluating generated text or images or videos is definitely something we have to improve in the future, because it's just a lot of time very subjective, and most of the current evaluations are just based on human studies. If you want to test it yourself, you can scan the QR code. We have built like a ChatGPT interface where you can just input a video and you can just ask questions and have a conversation with our model. It works quite good with our SoccerNet video data. If you want to try it with your own data, it's probably not as good because it was never trained on it. Thank you very much for your attention. If you have any questions, feel free to ask. Thank you, Jan, for these presentations. Are there any questions in the room?
say 60% for referee.
Yes.
Is that quite low?
No, not really. If you have a look at all human studies that are done in this topic, it's always between 50% and 80%. It always depends a little bit on how many views you are giving the referees. It depends on the difficulty. And a lot of time it's really difficult to determine if it's now a yellow card or red card, because it's like just if the speed is a little bit faster, it's a red card. If it's a little bit slower, it's a yellow card. And it's really a difficult task. So 60% is actually quite good. Yes.
No, if the referee are like 60%, how do you get, where goes your ground?
As for the ground truth, it was me who annotated all the data. So it's definitely a little bit biased and not 100% correct. But I mean, for first proof of concept, it was perfect. But if you want to really use it in the future in games, you definitely have experts who say, okay, this is now yellow card.
Question about you like prepared embedding before feeding that into the model. So you said 5 seconds videos, then you calculate embeddings for frames, and then you average them vector embedding.
Yeah.
How often you probe within that 5-second video? Isn't that averaging kind of like ruins everything with longer video?
So we never took the whole 5 seconds. We just took like, I think in total we gave an input of 3 seconds, and we in total it was like 25 frames. So I think to average along the temporal dimension with 25 frames is fine. But if you really want to have a video with a minute long, you definitely need to find another strategy how to input this temporal information. But I think for 25 frames, it's fine.
Because right now we precisely say when stuff happens.
Exactly, yes.
It's kind of like the complexity of it.
Yes, that.
While training your model, does the output completely come out of text in terms of how, in terms of whether it should be rectified or not, and the explanation? Or do you also try to train the intermediary latent representation of your embeddings, maybe using human poses or something like that?
Sorry, again?
Okay, so my question was, while training your model, do you only train on the output text, or do you also train your latent embeddings using human poses?
No, we just fine-tune clip. So the first step was just fine-tuning clip on classifying if it's a foul or not and the severity. Then in the second step, we just fine-tune this large language model to output an explanation which is actually good. But clip was first pre-trained on classification, on classifying if it's now a foul or not, and the severity. And then large language model was fine-tuned on making the explanations.
Okay, and then those explanations were not provided in the input while training?
No, we just trained on the explanations, but they are never given as input. Yes.
Thanks for the great talk. I'm actually curious if you tested it on situations where the players dive, like they fake a power. Those are the annoying situations when you watch a game. I'm just curious how you've tested this model on these situations.
Yes, so the dives, it was one of the classes that is very underrepresented in our data set. So I'm not 100% sure that it's detected a lot of time, but we had a situation where the attacker dived in the penalty area, and our model actually says it's not a penalty because the attacker was trying to deceive the referee by falling down without any contact. So it actually works sometimes, but as it's not very represented in the data set, if you really want to use it in an actual football game, you would need a lot more examples to train the model on. But even with not much or not many examples, it already works sometimes and also quite good. Maybe we have time for one last question. You can pick.
You could use the model now to collect more data. Verifying the results of the model would be much faster than waiting for the database to run it take 1 year.
Yes, but I think our model is not yet at a level where it produces that good outputs that you can use those outputs to train it again on. Like, as you have seen, it's just 58% or 59% accuracy compared to the ground truth. So if you would generate new outputs and train again on them, I think you would not get.
Manually remove the faulty.
Oh, yes, yes, definitely. Yes, that's true. Thank you very much.
Right.
Thank you very
I feel
much.
like more hands, but I cannot accommodate for the questions. So feel free to reach out to the poster session this afternoon. Thanks again, Jan.
Thank you.
We have one last speaker for today. PeterNet powering the Moneyball evolution of baseball video analytics from Jeremy Bright. Yeah, please.
So, Jeremy, the floor is yours. Yeah, thank you so much. Hi, I'm Jaren. So, I'll be presenting my work on PictureNet, with powering the Moneyball evolution in baseball video analytics. So, the motivation behind our work is to analyze pictures from the kinematic information, and this could be used for performance optimization, injury prevention, quantitative analysis of player mechanics. So, coming to prior works on baseball analytics, so there is two prominent kind of works. So the first thing uses pre-recorded baseball data, where they use databases like pitch effects, which basically has a lot of pitch metrics, and these pitch metrics can be used to find different actions. And the other option is to use data from controlled environments with mocap systems, icons to find the ports and then derive actions or different pitch metrics from these. So some challenges with the big input video data that can be used to train models or motion blur, self-occlusion, and out of distribution poses. As you could see highlighted in purple here, in the 4 frames where the pitcher is actually throwing the ball, the pitching hand, which is the right hand here, isn't visible. So it's very difficult to model the 3D or 2D pose from this kind of data. And there are a lot of self-occlusions as well, because of the player's movements. And there is out of distribution poses. So mostly pitchers tend to pitch the ball above their head. But sometimes there are pitchers who tend to pitch closer to the ground level as well. So if the network isn't trained in these out of distribution poses, it tends to fail as well. So the objective of my work is to enable detailed analysis of pitcher dynamics from human models in 3D. And this has to be extracted solely from monocular broadcast feeds. Right. It's okay, it's fine. Yeah, that's fine. So the high level workflow of the algorithm is to feed in the pitcher's broadcast feed. I'm sorry, the broadcast feed of the baseball game. And we have the data processing pipeline, which basically isolates the picture and estimates the depth of the person as well. And these data are then fed to the human modeling pipeline, which estimates the 3D pose, the 3D human model, or any human parameters. And these are then fed to the action recognition pipeline, which estimates the pitch statistics. So before going into the work, I would just like to touch upon the 3D human model, about what 3D human model is. So 3D here we have used something called SMPL, which stands for skinned multi-person linear models. And the idea behind SMPL is to represent any human, irrespective of the pose, with 82 parameters, in which 72 are joint parameters. Here, the 72 joint parameters correspond to the rotation between different joint angles with respect to the template, which is shown in the leftmost corner. And the 10 shape parameters corresponds to the height of the person, weight, and other shape-related constraints. So with this 82 parameters, they tend to estimate 6,890 vertices, which can then be meshed together to create 3D models as shown here. And so the definition here would be to use the broadcast speed as input to find either these 82 parameters or the 6,890 vertices. Yeah. So in order to do this, we propose the PictureNet system. And here the objective is to find the picture tracklet from the broadcast feed first, and then use a 3D human modeling pipeline to model the 3D human, and then do action recognition on this. So to identify the picture, the first thing we do is object detection with YOLO models, and then we track these detections to create different tracklets, and then we feed these tracklets into the role classification network, which finds the picture tracklet, and then we estimate the pseudo depth for the picture tracklet and feed all this together to the 3D human model, which estimates the 3D pose, and these 3D pose are then fed to the TCN model to find the pitch analysis. So firstly, coming to role classification, the idea is to decouple actions from the player kinematics, and the input would be the pseudo pose from the estimated tracklets, and the output of it would be the player role. If it's a pitcher, batter, referee, fielders. So here we use n blocks of T-con layers, which is just a combination of 1D convolutions, batch normalization, and ReLU activation functions. And so here, one advantage of using something like this would be it's invariant to viewpoint, and we don't really track facial features to find classify the player, and we do not require player jersey numbers. The only catch would be that we need the player role to be unique. For example, it could be used in cricket to determine if it's a batter or a bowler. Similarly, it can be used in baseball to find a referee or a batter or the pitcher, but not in sports like ice hockey or soccer, where anyone can do any kind of actions. So coming to the 3D human model, we'll build upon on model that we previously proposed, wherein we feed in the input image and the depth map as input to a transformer encoder. And it consists of a lot of self-attention and cross-attention blocks. And the output of the transformer encoder would be the 6,890 vertices. And these vertices are then fed to a distribution model rather than regularizing it using MSC or MSC loss or sort of. So the idea behind distribution matching is to so once we have all the output predictions, we try to minimize the deviation in the distributions of the predicted and the ground truth vertices. And using this, we were able to obtain generalizable 3D humans, which I'll be showing in the coming slides. And we also included motion blur and in the wild data augmentation to improve the performance on extreme motion blur conditions. So coming to pitch analysis, we focused on finding 4 different pitch metrics. The first thing is the pitch position, which is just before they release the ball. There is a wind up and the pitcher set, which we try to find. And for this, we use the same TCN module that has been used for role classification. And then we estimated the release point of the ball. For this, as you could see in the left-hand side image, there are 6 phases of the pitching action. And you could see the trajectory of the right wrist, which is the pitching hand of the pitcher in 3D space. And we consider point B, which is where the arm is, from where the arm is going to decelerate. And we hypothesis that the release point is going to be n frames around the point B with the maximum velocity. And yeah, to find the pitch velocity, we find the angular velocity and pitch velocity and extension are calculated just from the kinematic output that we have from the 3D human model. And pitch velocity is computed using the computed with the release point and a frame before that. And release extension is basically the distance between the wrist of the pitcher and the leg of the pitcher at the moment of pitching. So if I go back. Yeah, if you could see in the wind up image, the G here, so it's the point at which the pitcher has his leg on the pitch mount and the release point of the ball. Since we know these frames exactly, so it's easy to calculate the release extension. So talking about the data set, we have more than 1,000 games, and each and every game consists about 50 to 100 pitch sequences. And all these data, we do have various pitch metrics, ground truth for these data as well. Yeah. So going to some quantitative results of role classification, the first thing we compared it with baselines, LSTM and transformer. And then we also wanted to compare the performance of our role classification with different jersey number techniques. And our work was able to consistently outperform existing works. And coming to the quantitative results of 3D human modeling, we compared it with two benchmarked data sets, a human 3.6M and 3D PW. And our results was consistently better, and we were able to obtain the share of the earth in human 3.6M data sets. Going to the quantitative results on the pitch analysis, we did a study the performance with the 5 pitch metrics that we estimated, and these are all accuracy with different margin rates. So yeah, it did perform consistently better, especially with handedness, pitch position, and release point. Our network was able to very robustly find the results. With respect to, especially with respect to release point, it did have high influence on the motion blur, did have some influence on the results. And I'm not able to show this video, but we did, that's right. Yeah, so we did want to show some qualitative results of the 3D human model with different broadcast data, like for basketball, ice hockey, boxing, and different. And yeah, here we do show some results, qualitative results for pitch analysis. Here you could see the 3D human model is overlaid on the person, and we did show the prediction and the ground truth pitch metrics. And yeah, to summarize, we are proposing a reliable pitch analysis framework, which is driven by player kinematics and human model priors. And we also proposed a role classification network, which aims to classifying players by decoupling their actions. And we also proposed a refined version of one of the existing works that we proposed, which aims to model 3D humans in degraded image quality. And yeah, thank you. And it was partnered by.
All right. Thank you, Jerry, for the amazing presentation. Impressive result as well. Congrats about that. And I'm very sorry for the videos. Please, I invite everyone to go to the poster. Maybe you'll have a copy of the videos. Sure. Are there any questions in the room? You are between the lunch, that's why. So I do have a questions. You tried that on videos that you created a data set out of it, and you tested all the performances of your methods. I believe those are somehow professional broadcasts.
Yeah.
In the talk of this morning, we also had the insight of there are also some lower leagues that exist in the world that have more people working on. Do you think similar methods would work? And if not, what are the challenges in order to give that to the broader audience, this type of techniques?
Yeah, so primarily for us to do analysis, so this is done on behind the pitcher viewpoint. So if we have similar data from behind the pitcher viewpoint in any stadium or any league, this algorithm has to work. But we have noticed that when we change the viewpoints completely, when if it's if it's on the home plate or on the second or third base, second or fourth base, there are some deviations in the results. But I think those can be improved upon by maybe if we get access to data from different viewpoints, or maybe creating synthetic data as well. So that could be the approach to go forward with that. Yeah.
That's a very good point. Any other questions in the room? No? All right. So thanks again, Jarin, for this presentation. Thank you. Yeah, you can. A few announcements before we adjourn. There will be lunch actually provided, but I think it's in the other building in Summit. Mind that there is, I think, a 15 minutes walk from here to there. So we're gonna be back. I mean, the work we need to go downstairs. Anyway, we'll be back here at 1:30. We have a presentation from Mirko Messori from Sfera. It's an exciting talk about new sports. I don't want to tell more about that. And it's nice how new markets can actually introduce new technology. So I would invite you all to be back here at 1:30. Another announcement. Well, of course, take the opportunity to network with everyone in the rooms. I mean, you see the faces, you see who are there. The lunch break is also an opportunity for that. For the spotlights and the poster of this afternoon, we have put the number of the poster in the website. So I invite you to go to the CV Sports website, Google CV Sports Workshop. It's a first website that should pop up. There will be an ID for your poster. This is your ID as well. If you have not shared your slides yet with me, the 2-minute slides, please share them. And I'll be here now if you want to test them now to see if there is no issue with videos or anything, so that we don't have the same issue that we just had before. Thank you.
Allora ci vediamo dopo. Non abbiamo capito per parlare proprio questa alla fine di presentazione per riguardo la
Yeah.
Devo dire che dopo mi ha chiesto degli stakeholder per
approach for to make something in 11 and like until 2018.
Okay.
Yes, like we're trying to have the small boxes that we can then assemble to do bigger stuff, and then apply a bit of learning on top. And so I really like that together.
Thank you.
Yes. Look at them there. Well, thank you very much. You have all the email address, phone number. Check. Yeah. Contact me on WhatsApp.
I think that's the main purpose. I think. I mean, I don't want to like we just had that slide. So
hey, yeah, right. Maybe you have.
All right, so the last spotlight here. And which one is yours?
Can I step? Yes.
Yes. I've got all this. Yeah, we send it like recently.
That's fun. I'm very surprised. That is by leveraging what's called fair use. So the data is copyright, right? So you cannot use it for commercial application. So the way we usually do that is that we first say it's for research only, which falls into one of the 4 pillars of fair use. It's like it has to be not non-commercial. Then the data is limited compared to what the game is. So yeah, right? And we have people sign an NDA. Saying that's there, you cannot distribute it. YouTube. They can only do for academic purposes, and that's it. And so basically, solving into this very use is how we might be difficult. We have like Google side as well. It's really academia because there is a lot that says, especially in Europe, I don't know if it's worldwide or not, that can prevent someone from doing research just because something is theoretical. This is like a liberty of academia that we have in Europe, and we're leveraging that. So be able to share it. Playback. Yes, we were actually not able to extract it from people. Was able to do it in 2020. I started working on the project, and then they had an update. That's a block the pipeline. We had to go to but this is more like the game. Yeah, they protected it very well because it works with GTA 5, you know. Hello, nice to meet you. It's with also Euro Travel later. We tried it with a lot of but yeah, people protected their game too well, and I cannot get into it. But for the other games, it's hard to considering the similar idea, but it's the good one extra. So the gaming issue can follow up using the NVIDIA. I don't know if that, I don't know if you get lots of we here provide the information, but actually you get mature. Okay. Sometimes like the games, not sure. It's like you can get all the textures, all the 3D, but they are encoded. So it's very difficult to know where to look for the data. Actually, you get the whole recreation of the whole scene, everything step by step with the graphics inside graphics. It's a bit more complicated to parse, parse for sure. Okay, but if you're interested, definitely get in touch because like a gift, or is it like we release the videos, you also extract the data. It's available. You can check it out on the. I think it will be available on the org website. Otherwise, I would check the poster in the afternoon and we'll see also. Thank you. But yeah, definitely there is something on the release also very good, not only extract the data, but all the 3D of the scene and the outcome to do. More like not good friends. Yes, I so many times I was feeling good. We have been working. Oh yes, true. Yes, yeah. It's only so I use pick up interest also in the person. I know the names. So this is a reason why. Yeah. And also because I don't know if you remember from 2018. Oh, you have it. This is really great paper. Soccer on your tabletop. With AR glasses, you could see your soccer game. It's very early work, and they use that estimation in folder rule able to do that. Oh, yeah, if we need that for so. And these guys, they did it with fields very sharp. They have that they never released the data because they were in collaboration with it's not like the teaser, of course, like or the different and they need to tool with so we figure out like let's put an open source tool for anyone who's interested in that. I don't have video. No, I have other video. So you're working, also like for the environment. Yeah. Find a way. Instead of really the range is simulated and still similar. It's good. Like simulated and also like useful data and we all want that. Just get it, make it work. You make it work. Send it yet. Okay. Limited amount. I haven't sent it yet, so you're send it. You can thank you. So in a way, or even have a USB stick or something. Hey, hi. Yes, yes. Okay.
Oh, yeah, it's actually
Very good.
Yeah, that was very.
Yeah. Stuff really it's
Weird to me, like, it's fine. I feel like between
Weeks of sports, it's like,
Yeah.
I'm too.
Yeah.
One, I know we're not watching the Euros, but we're still present.
Yeah, I know. Like in 2018 CVPR, they used to put a big wheel and
I was wishing that.
yeah, I don't know why they.
There's people in there.
because like slowly the older somehow on settings.
Not supposed to. It's the jungle.
Yeah, yeah,
I was like extremely jet lag. I was sleeping and he woke me up.
Nice.
I have a very interesting question for that. I was the only one with the advice fee.
Okay. Just order.
Yeah. Like guys also. You register. You register.
Oh, yeah. Try it.
Okay.
So we're opening it. Oh, you're looking rugby.
I don't know. It's because not, so it's waiting list, and then they're gonna select, but they prioritize all the others. So
You're from you.
yeah, for sure.
So see you later.
I mean, I get a better Japan name. Hey, there were the work test, right? I mean, there were actually like, but
Yeah, the previous one wasn't. Yeah, the one before.
Yeah.
Well, it was in Japan, so.
yeah, it was in Japan. I mean, like the secret investigation app, like vision language. Oh, that's true. I remember like a year ago, there was like people from South Africa that were working on question.
Yeah. I think that's, yeah, we are actually working on a national project. And to do that, we need to classify define the tackle scene. So that's why I brought yeah. So that's not said in this presentation.
Yeah.
Out of the scope of this paper, but yeah.
That's really cool. Well, yeah, I currently work for football with feedback for head injuries analysis.
Yeah.
Like some work. We published a work I think last year with them. On football. And we like really a lot of concerns about compression, like tactical get better right. But definitely like rugby is the place, like they actually have protocols for that.
And then the players hide. The situation. They don't want to be detected that they have a concussion.
If we
Play football. So that's yeah. Used it.
Well, I used to
if I play at least I get injured.
That's fine.
Yeah.
That's cool. All right. Looking forward to that as well.
Thank you.
And thanks for sharing.
Thank you for the organizing.
Yeah, thank you for participating. C'est cool.
Et ici,
Genre pour
genre M, tu crois que c'est bon pour elle? Pour qui? Shaima et Justine. Ça c'est M aussi. Moi c'est M aussi. Ouais, ça devrait aller.
C'est du M femme ou M homme?
Il n'y a plus que
Ok.
ça va être moi. On va demander à Maxime, c'est la seule qui l'a vu.
C'est ce que j'allais dire. Parce que t'as pas autant de tech que Justine, je pense. Mais bon, voilà. On met ça, disons, manière.
Je crois que ça. Ouais, alors,
on vous fait ça un peu.
J'en ai pris un pour Céline aussi, du coup, comme il restait pas mal de S. En fait, il reste quasi plus de M, mais il reste beaucoup de S.
D'accord. Bon, bah, je me suis manger un bout. Il y a personne qui vient ici. C'est ça ici, je sais pas. Tu prends ton cadeau et ton laptop et tout.
Moi, je mets sous le.
Je pense de la flemme.
Si on le met, tu vois, sous le.
Sous ça. Ouais. Moi, j'ai grave la flemme.
Je vais juste prendre ma veste parce qu'il fait quand même un peu froid dehors.
Ah ouais,
c'est bien. Il est cool les talks ce matin.
Ouais, c'est vrai. Qu'est-ce que je peux faire, moi? Ah putain, j'ai débranché ça. On est toujours en dessous.
Faccio l'audio che ci sentiamo. Prova, prova. Dico che passa, non c'è che rispondere. Sì. Ok, perfetto. Pratica questo microfono. Ci sentiamo. Aspetta, io ti aiuto anche a chiudere il corso ormai. You can minimize it. I can night from this working so they have shared the entire screen. Yes. Ok, per shortcut questo è il live, questo è il qua. Ok, vi presento in questi minuti. Mi presenti tu? Ricordami, Sfera founder, CTO, come ti puoi dire? Io sono CTO, ok. Sei CTO anche founder o no? No, vabbè, founder. Ok, perfetto, non lo CTO, poi vabbè. Right. Hi everyone, good afternoon. Thank you for coming back for lunch. I hope you have eaten a good sandwich, a good salad. You've had the time to come back to digest, grab a coffee. I recommend the Starbucks coffees from Seattle, by the way. It's really good coffee. Like usually TVPR, we used to have like really bad coffee, but this year is actually okay-ish, I would say. From the Italian perspective, I would say average. But thank you for being this afternoon. Right now, we're going to have a talk from Mirko Messori. Mirko Messori is the CTO of Sfera. Sfera is a company based in Italy, Milano, and working on something quite interesting, particular a new league called the Kings League. And I think it will be quite interesting. Sfera is also the sponsor of that workshop. So we thanks again Sfera for their trust. Looking forward for your talk. Mirko, the floor is yours.
Thank you. Thank you, Silvia, for the presentation. Good afternoon, everyone. We had to fix some issues in production. Huh? It's very common when we have to deal with clients to fix something in production because there is always something that we did not test sometimes. Anyway, so today I'm talking about Sfera and the Kings League use case. Kings League is a new sport. We will talk about that later. Before getting into the presentation of what we are doing for Kings League, I would like to give you a little bit of color of what we are doing and from where we started. Sfera is a sport tech startup based in Milan. We are pretty young. We started in 2021, and in the beginning, our mission was initially to assist football stakeholders in transitioning to data analytics-based model. So practically, we wanted to give to people that is working on the sport field quantitative instruments that could support their decision. For instance, you can think about the scouting, right? And other fields like players trading and also the calculation of statistics. We don't have so much quantitative data and quantitative instruments. At least this is true for the Italian market because we are based in Italy. So actually our main focus was the Italian market. And so our goal was to provide to our clients such instruments. And first of all, the main important topic that we would like to consider is also to keep the costs low, because if you go to the major leagues like A series, we talked about that this morning, they have infinite money. They can invest whatever they want in hiring people and buy cameras and everything. This is not true for the minor leagues. So actually, part of our goal was actually to provide those instruments to the minor leagues. So I will run through our technology overview before getting into the Kings League use case, just to give you a little bit of background. Sfera is not a front-end company. We are doing just back-end. So we are not providing like GUI or a user application that can be used by the public. Our clients are mainly other companies. So we are mainly a B2B company. And so this means that our main effort is on the back-end. And not only that, you can see in this table that is divided in two main parts. On the right, you can see the backend, that is everything cloud-based. We are using, by the way, AWS. And on the left side, we have also a part that is called on-site acquisition. Why? Because actually part of our goal was also to provide an hardware that was actually low cost for clients that were requiring us to give them instruments actually to measure data. Measure data means doing annotation or also just providing videos, right? Because in minor leagues, in most of the field, you don't even have camera. So about the video acquisition that I will introduce just briefly what we did in the beginning. This was actually our main topic back in 2021 and 2022, when actually our effort were concentrated more on on-site acquisition and on the hardware. We provided a solution that is based on security cameras. So practically our objective, as I said, was to keep the costs low and also to provide to our clients hardware that was easy to buy in the market. You have to remember also that just after the COVID, at least this was true for Italy and Europe in general, we were living also a crisis of the microchips. So it was very hard to achieve the proper hardware to be installed in the field. So actually with this compromise, we decided using actually security cameras that of course have been modified. We have installed like some antennas on them, and we have developed also power units. This gave us the possibility to install this hardware and to provide our clients various resolution and various frame rates. In the picture, you see actually a camera that is provided by Axis. This is a 60 FPS camera that we are actually thinking using on paddle. I saw this morning that paddle was actually the last piece in the last.
It's a new sport, that's why.
Yeah, so actually, but I will not talk about paddle today. So this is an example of the installation that we did on an indoor field in Carugate. Carugate is a very little city close to Milan. It's just 15,000 people, so not so big. And as you can imagine, the Carugate team that is part of the Series C1 does not have any money to invest in this kind of stuff, right? So actually what we did is that we provided them one of our solutions. That camera that you see on point number 2 is provided by Vision in this particular case. And what you can notice in this case is that we were not allowed to attach our system to the power network of the field. This is an indoor field, and since the field was actually owned by the government, you need some special permissions to just attach your system to the network, to the power network. And so since we were not able, because of Italian bureaucracy maybe, to get such a permission, actually, we provided a solution that is autonomous. And on point number 3, you can see actually that there is the power unit in which we have installed batteries that can cover an entire season before getting recharged again. And you can see in point number 1, actually, there is an antenna. Why? Because we cannot actually install cables where the people is working, right? When it's looking on matches. So we have also to face security regulations. Let's go towards the main topic of this presentation, that is the Kings League. In addition to the on-site acquisition that I was talking about now, we provide also all the backend. So the cloud-based infrastructure that is needed not just to install hardware, but also to get the data, to gather the data and to elaborate it. And about cloud infrastructure, I'm going to propose you just a couple of structures that we have developed for a couple of clients. And the event spotting, that is the one on the bottom, is the one that we actually have provided to the Kings League. Before talking about the event spotting, I would like to introduce a little bit what we did, for instance, for Carugate, mostly used for tracking the players. As you can see, practically, this tracking infrastructure on top is actually providing cameras in the field. So we have seen the installation in the previous slide. Those cameras are attached to a local storage. The local storage is practically storing data in a compressed format. And these data, these videos are then uploaded into cloud. We are using S3 for cloud archivation, for the video archivation. And then we have provided EC2 computation for codec conversion and video decompression. And then, of course, we have developed a few models. Actually, to be honest, we did not do so much work on deep learning and modeling, because actually we need to face also for what our clients are asking us. And so we need also to optimize our cost and dedicate our resources on what the client is asking us. And in any case, we were able to provide some basic models that are running on SageMaker. And then we expose via Gateway some APIs that our clients can call to gather some data. As you can see, we don't have interfaces. We provide the client an API, and then it's just a matter of the client if he wants to integrate this API in the front end or something like that. In the event spotting case, that is actually part of we did for the Kings League. That icon on the top is the Kings League icon with that face king. Is another infrastructure, and that is actually explaining why we decided to use cloud infrastructure, because actually it gives us enough flexibility to adapt our systems to the various clients' needs without actually requiring to buy new computers or new servers. You just turn on and turn off some virtual environments and you're fine. In this particular case for the Kings League, as you can see in the field, we don't have any camera, because in this case, the Kings League has its own cameras. And what they were asking us was to provide at low cost events annotation of the matches. And events annotation, I mean goals, balls, each single pass, and also there are annotation that are referring to some modified rules that we will see later, because this is actually, as we will see later, this is not properly soccer, it's a modified soccer. So actually there was also an issue about customization. Practically we were facing a sport that has some rules that were never seen before. So actually in the market, it was not possible to find any program that was dedicated on tagging events of that particular sport, because that sport is new. So what we did is that, again, by using AWS, we have used, in this case, Amplify to deploy an application developed in Angular that we provided to some of our people that we send in loco for looking at the matches. And then we ask these people that are working for us to tag the match during the match is live, not during the match. And practically this is sending the data into a high performance NoSQL database, the so-called DynamoDB database of the AWS, that is a NoSQL key value database. And as you can see, the Kings League, even during the live, is able to call our APIs, because during the live, they want to show to the public some real-time statistics like the ball possessions or the number of falls and so on. And this is possible thanks because we are sending people that is actually tagging stuff. We were able to send just 2 people for each match. So if you think about it, it's a huge cost optimization, because normally what you see in that in the minor leagues, you never see people tagging data because it's too expensive. Actually, we were able to provide our clients such kind of a solution. And then we are also providing a subset in the post-match elaboration that is practically, if you think about it, when someone is like tagging the match, you cannot ask to the tagger that is looking at the match to tag for each single pass who is doing the pass, because there is no time, right? Indeed, we have the differentiation between the blocking events and the non-blocking events. A goal, for instance, is a blocking event, because after the goal, the match is stopped, and actually you have the time to tag who did the goal. But for the passes, you just press pass, right? You don't have time to do so. So that's why we are providing also so-called post-match elaboration. That means that we have developed a program. After the match, we are able to load all the annotations that were tagged live, load the video that in this case is provided by the Kings League, synchronize the tags with the video, eventually correct some errors, or add also some missing events, tags, or additional annotations that were not tagged by the live because they were too complicated. For instance, if you think about the duels, it's very subjective, and normally when you are like concentrated in looking at the passes and the falls, you cannot even think about this was a duel, was an aerial duel, or something like that. So these actually are stuff that we are leaving to the post-match taggers. And in the end, the client, in this case, the Kings League, has the final video with the annotated data. Just summarizing what I have introduced before, this is an example of the output that we provide to our client. In this case, this is a view of the Carugate indoor field. This is just an example of the tracking output. I don't want to deep dive into this because of a matter of time. But now, as promised, I would like to deep dive into the Kings League. An introduction was needed anyway, because it's a new sport. It's difficult for me to. Okay. So I would like to emphasize here also what we are talking about when talking about the Kings League. If you recall the slide that I was showing in the beginning, I was talking about an on-site acquisition layer and the backend elaboration layer that Sphera is providing to clients. In this particular case, as you can see, for the Kings League client, we are provide on the on-site acquisition side live data annotation, and on the backend elaboration, we are providing actually post-match data annotation that is actually an elaboration that is done after the match. So what is the Kings League? The Kings League is a new type of soccer, okay, that was founded in 2023. So practically we are talking about last year. And the main sponsor was Gerard Piqué. Ex-wife was the singer, right? and Gerard Piqué was the main sponsor of this league in the beginning. Now it's no more true because, of course, this is becoming more and more big. In the beginning, this was founded like in Spain. Then, as you can see on the top of this screenshot, this is the official website of the Kings League, but there is also Americas, not United States, but mainly Mexico. It's arriving in Italy this year, announcing September 2024. And there was also the World Cup that was finished on June 9, 2024, so less than 1 month ago. And as you can see, how many people attended the final of the World Cup at the stadium, more than 50,000 people. So actually it's getting more and more interesting. And we have also teams that are new teams that are playing, let's say, this championship. But inside these teams, you can recognize also Totti, right? So practically, we have former soccer players that are participating as well with the people that wants to play this game. And now you maybe are wondering, what is that dice? All right. Okay, as I told you, Kings League is not like a regular soccer, it's a modified soccer. And the dice is an example of how they modified the rule of this game. The dice rule is just one of the examples, but the dice rule means, okay, the Kings League is divided in 2 halves. Okay, the first half is 20 minutes, the second half is 20 minutes as well, and we have extra time. The time is divided in match time and absolute time, like the basket. So actually, they stop the chrono every time. Maybe there is a foul, something like that. But at minute 18, that is when 2 minutes are missing from the end of first half, there is this dice rule. So a YouTuber or an influencer are normally called and just start throwing this big dice in the middle of the field. And based on the outcome of this dice, practically the number is deciding how many people in the field will play the game for the remaining 2 minutes of the last of the first half. So practically all the people want that the numbers are be 1 or 2 because they like to see people that are running that are alone. Practically, you have to run a lot. And so yeah, this is just an example. And as you can see, to provide a service of annotation, we had to develop something custom, for sure, of course, because there was no concept of dice, right? There are also additional rules like the cards, but I mean, we don't have time to deep dive into all the modifications because I think that the dice example was a nice one to talk about. And what we developed is what you see in the top left corner of the screen is a screenshot of the front-end application that we give to the guys that were sending to the field, looking at the match and tagging the data. This is a picture that was taken during the World Cup in Mexico. And as you can see, we have the possibility to give to the client a notation, and the client can calculate some real-time statistics, like in this case, we see an example of the ball possession, right, that are shown during the live, okay? There is also a goal per two on the top. That's another rule. Sometimes the goal score two. So that's another modification of the rule. We have this part of the games where actually if you do one goal, you score 2 points. So yeah, that's very nice. It's very interesting to see. This is an example of the program that we did for the post-match. Again, everything is based on cloud. So this program is actually connected to our cloud environment. As you can see, the violet button maybe is not very clear, but these are, for instance, button of the Arma Secreta. An Arma Secreta is another custom rules when you can play like an Arma, secret Arma, but yeah, you can deep dive later if you want offline on what does it mean. But the concept here is that we had to develop something custom, okay? And in this interface, you can see that we have developed something that can minimize the amount of errors of the taggers when reviewing the data. You can see that, for instance, on the top, we are showing the goals that are calculated based on the events, so you can verify that everything is in line with the video. On the bottom, we have some buttons that are used to adjust the time, so we will need to provide the client events that are very aligned with the video, and so very good quality data. We actually do 2 to 3 quality check before releasing the data to client, because they are very, they want the data to be very precise. And so here what we are gathering is a very high amount of data of high quality. Now, I just want to cite Roberto, because Roberto is the founder of the Kings League. Sorry, not the Kings League, of the Osfera. And I want to thank him because thanks to him today I'm here to present Sfera. And we need help because we have too much data and we don't have enough people now to work on this data, right? I heard this morning that most of the applications that you are developing can be improved thanks to the data. Okay, we have data. And so that's why also we are sponsoring this paper award, to make available this data to everyone who wants to try something nice with our data. And that's it. Sorry, it was longer than expected, but that's it.
Thank you, Mirko, for your presentation. Are there any questions in the room?
Yes, please. Yeah. Keep in mind that today we are actually providing to our clients any type of event they want, so even more complex events, but we are tagging them manually. We don't have an automatic system today that can support the automation of these tags. So main point here is that we have a lot of data. We would like to develop something that will be nice for us to at least not having something that is 100% automated, but even if it is semi-automated, think about our taggers, right? Now they are doing everything manually, but if we have a model that could help them in a semi-automate their work, this will result in actually in a further cost optimization for us. So this is, in my opinion, an example of how you could use models in industry, because this is actually a requirement that is arriving from a league. So if you have good models, please contact me and we can have a collaboration for sure.
Any further questions? Yeah.
What's the viewership like? Many people watch this online?
Well, it depends if you go to the Spain League or the World Cup League. During the live, I remember during the final, there were like connected 150,000 to 200,000 people in Twitch and YouTube. And then during usually the final is done in a stadium. We had at the beginning of this year, we had the final of the split three on Malaga. The stadium of Malaga was full. So practically was very full. And now the World Cup final was in Mexico City, and the stadium registered more than 50,000 people. So actually it's getting a lot of audience and is increasing over time. It's expected to increase again. Now it's arriving also in Italy. As you know, in Italy, people is extremely passionate about soccer. I don't know if they will be passionate about the Kings League, but we need to try and we'll see.
Any other questions in the room? I do have a question for you, Mirko.
Yes.
I mean, there is a lot of researcher here, and they're providing a lot. They can provide you with a lot of technology. How much appetite there is for Sphera or for the Kingsley to actually implement this type of technology? Is it something that they are eager to, or they are more reluctant to? What's their opinion on that?
Well, the answer depends if I answer as Sphera or as Kingsley. Okay. If I answer as Sphera, we are very interested, and I'm telling you why. As Sphera, we want to optimize our cost, and optimizing cost means having people that is working less amount of hours to achieve the same result. To do so, we need, of course, anything that could automate some manual task, even model-based. If I would answer like a Kingsley, I would answer, I don't care, just give me the result. Because they want the result. They don't care if we spend nights awake in manually tagging the data, or if we provide them semi-automated data. The important thing is they want quality data.
So they're still eager from the data, so they want this data. So,
yes, yes, because of course they are constructing the market of the players. They want to base everything on quantitative data.
Interesting.
On my side, I have another question that is both for you, but also for the audience. So I will ask for your opinion on this. But if Sphera were to provide those data and annotations, would there be interest in the scientific community as well to, for instance, organize challenges and participate in those challenges to develop the best technology, a bit like we're doing for soccer right now? So by a raise of hand, like, would you be interested in working on such data from the Kings League? All right, very cool. So this is maybe something we can talk about.
There's another question here.
I have a question. So you talked about different ways to make it more economically responsible for the company, and obviously there's a lot of processing that goes into building models like that. So what were some techniques or creative ways that you found to cut the cost of storage, storing all of the data and analytic processing?
Well, the storage as of today is what is costing us less, because we are using a S3 service of AWS that is one of the most economic services that you can find in cloud. And so practically, we have also different classes of data. So when we needed to work on some videos, we store them as a standard class that is a little bit more costly, because they are like billing you for each terabyte that you are storing. We are talking about terabytes, so actually you can store a lot of video. And the oldest matches, we can modify the class from standard to what they call the infrequent access data. And in that case, you don't pay anything. You just pay when you need to access the data. But if the data is not accessible, almost you don't access this data, it's not gonna cost you so much. So actually, for the archivation point of view of video, we are fine. Thank you for the question.
Any other questions in the room? All right. Well, thank you, Mirko, for your presentations. Thank you for being here with us. And let's have a round of applause for you.
Thank you.
Right. So now we're gonna move on to the spotlight. So can I invite all presenter of the spotlight session to align across this wall there? Maybe in the order that is presented on CV Sports, but don't worry, I will go through. So how it will go is that you have 2 minutes to present your paper. All the slides should have been sent to Silvio before. And so it will launch your presentation. You've got 2 minutes, and then you can take your seat. There is no question during the spotlights, but you will be able to ask your question to the authors during the poster session that is right after. So we got an exciting round of 19 presenters today, which is a lot and which is great. So I will leave Silvio to prepare the slides, and then we can start with the first person.
Yeah, just need a couple of minutes, sorry.
Thanks very much. Okay.
Actually call out the first person, which is Takeshi Kaneko from Tokyo Institute of Technology.
I think this is oh, maybe I'm confused, but
there is a first online presentation.
This is the first online presentation before we start. Sorry about that. Yeah,
I never felt like a little bit.
A lot of people. So the first presentation is from this team. It's online. Unfortunately, the person couldn't get its visa on time. Unfortunately, that's a recurrent problem in CVPR that we always like to raise awareness that some people cannot accept. Fortunately, attend CVPR for visa restriction. Fortunately, but this is the first presentation of the first presenter. The second speaker is Takeshi. It's Taniko. Thanks.
Thank you for attending my presentation. I'm Takeshi Kaneko. I will be presenting my paper titled Augmenting Path Prediction via Imitation Learning in Cycle Simulations. Path prediction is crucial for understanding player behavior and team strategies, aiding coaches and analysts in evaluating performance and formulating strategies. Path prediction using both trajectory and video data provides a comprehensive understanding of player movements and context. However, this approach faces challenges due to limited data, making it difficult to accurately capture layer and aggressive passes. To address these challenges, our approach uses synthetic data alongside real video data. We train a policy network with a convolutional we train a policy network with a convolutional neural network for behavior cloning using the football simulator to generate synthetic path scenes. This synthetic data combined with real data improves prediction accuracy. Our method shows a 3.72% improvement in top-down accuracy for predicting the intent path receiver compared to existing methods and successfully predicts a wider variety of paths. The results indicate that our method effectively learns video representations, leading to better accuracy, especially in scenes with significant body axis changes. Future work will focus on integrating inverse reinforcement learning and more detailed scene-specific data to further enhance accuracy. Thank you for your attention.
Thank you. And it will be in poster 106. So if you want more information about that method. Next presenter is Calvin.
Good afternoon, everyone. So this is our project to propose the automated 3D posture analysis of the soccer short movement. So in the previous research that we have seen, there are a lot of exciting theory techniques that have been applied to data annotations and even action recognitions, but there are very limited applications on applying those techniques to actually analyze the posture of the players, which is one of the fundamental of the sports. So to facilitate the development of the posture analysis, we have identified some limitations in the current literature. So the first one is the existing posture data sets like the MPII or the whole body data sets are general purpose data set that only provide the partial information like only an image. So first we propose that the pretty short posture data set that provided the 2D posture annotations and also the 3D posture estimation from the software model. And during the process of writing this paper, we believe that this is currently the largest 3D data sets for sports specifically. And for the other limitation on the posture analysis itself, a lot of previous analysis was done under simplified scenarios, and the data annotations were very labor intensive, and which is also linear model based. So we provided the auto post, which utilize a lot of civic techniques, which if you want to know more about the details, you can find us at the poster 107. And at the bottom, you can see an examples of how we could extract the 2D and 3D posture from the broadcast videos directly. So that's all for the spotlight presentation. Thank you.
The presenter is Maria from York University. Yeah. It's not yours. Yes. That's the one from poster 108. Yeah, 108. Yeah.
Great to be here. I'm Maria Koshkina from York University, Toronto, Canada, and I'm presenting our work on general framework for jersey number recognition for sports video. The main task that we're tackling is to detect and recognize player jersey numbers, both on individual player images and player tracker. And it's a challenging task since the jersey number is only visible for fractions of a frame, for fraction frames in each sport video for each player. And it's also often they're all fluted, blurry, the fabric deformation affects the detection and recognition, but it's an important task for player ID, player tracking, game analysis, and so on. In our work, we argue that jersey number recognition is really a specific case of syntax recognition. And syntax recognition is a well-studied problem with a lot of applications in that area. And we are reusing syntax recognition network for jersey number recognition. Typically, in a syntax recognition pipeline, first step is text detection, which requires bounding boxes around the text to train. We're sidestepping this requirement. This requires a lot of expensive annotation, and we're instead introducing a two-step approach. We're introducing a legibility classifier, which is binary classifier of the whole player image, or whether the jersey number is legible or not. And then we're just using off-the-shelf pose detector to crop out the torso area of the player before feeding it into the syntax recognition. We adapt this this pipeline for individual images into the tracklet level jersey number recognition by introducing additional component that filters out distractors and just leaves out the main subject of the tracklet. And then we combine the predictions from individual images into a single tracklet level prediction for the tracklet. We conduct our experiments in both hockey player images in the data set that we've annotated and will be making available. And we're also conducting experiments at tracklet level on the SoccerNet jersey number recognition data set. And we thank the SoccerNet team for the data. We report high performance in both settings, and I'd love to talk more about it at the poster runway. Thank you.
Thank you. Next speaker is Fahad from Hamad bin Khalifa University, poster 109. No.
Hello, everyone. Thank you for the contribution. Assalamu alaikum. My name is Fahad Majid, and I am from Hamad bin Khalifa University, Qatar. I am a PhD student, and today I will present ME soccer motion vector-based augmented instance segmentation for soccer player tracking. So this work is basically based on the it has basically three stages of backbone stages, and two stages are based on the backbone and neck, and then the future prediction analysis. This is the main architecture of our framework. So it is based, initially it takes input images 608 by 608 by 3, and in the backbone we applied CFP cross-stage partial network 3. And it has basically 53 layers for that. And after that, we applied net path aggregation network for that. And in the head stage, we applied in segmentation stage, we applied feature map. Once we get the data from the second stage, we convert those feature maps into we applied deconvolution for that, and then we converted those feature maps into gain images, and then we applied frame differencing on those images. We take previous frame and the next frame, and we subtracted those frames on the basis of frame differencing pattern, and then we applied motion compensation for that. So if you take so once we obtain the motion, we applied frame differencing. After that, we applied motion compensation, and then we applied more computed motion vectors from those, and then we gave them to the head segmentation head. In this scenario, we have basically 3 heads, and then we obtain different results regarding that. And in this work, we introduce new data set, and that is currently in this slide not available. You will take a look in the poster. I will introduce that, and that data set basically based on 47 different videos, and all of these some of videos we have taken from with 30 frames per second. Some videos we have taken from 25 frames per second, and some videos were taken with the 50 frames per second as well. And that data comprises of different 47 nearby games. And in next slide. The intuition behind applying motion vectors is that first, initially in the first 2 rows, if you take on, there are 2 static scenarios. And initially, the first phase there is RGB image, then we converted that image into Sobel filter, then we applied 3x3 Sobel filter over that, and then we converted those Sobel filter into color-coded motion vectors, and then we converted we obtained motion vectors from those edges. And the last row is representing the dynamic scenario, in which you can clearly see the difference between how displacement is happening and how we cover up the rest of the scenario. And this is the output we have then obtained. Thank you so much. Thank you.
Our next speaker is Nonaka.
Yeah.
Oh, sorry, technical issues. Next speaker is Naka, will be poster 109.
Hi, I'm Naoki Nonaka from Riken, Japan. Today I'll present rugby scene classification enhanced by vision language model. So we worked on rugby scene classification using vision language model. For this, we created a dataset consisting of 30,000 level images extracted from 5 elite rugby match video. Based on our experiment, vision language model with appropriate prompts improves the classification performance. Here's the brief overview of our datasets. So we labeled 11 labels listed here, and then using these labels, we conducted 5 classification experiments, 4 binary classification experiment, and 1 multi-class experiment. Here's the summary of experiment. First, using vision language model improves the performance of scene classification. And furthermore, providing prompts tailored to rugby tends to improve the classification performance more. We would like to have a discussion more in the poster. Sorry, maybe my poster ID is wrong.
110, sorry. My bad. Yes,
okay.
You're right.
Yeah, that's all. Thank you.
although mistake, the poster is 110, so let's try. Our next speaker is Arnaud.
So, good afternoon, everyone. My name is Arnaud, and one thing you should know about me is that I'm a big fan of video games. But I'm also a sportsman that has become really passionate about computer vision. So actually, that's three things. The reason I'm telling you this is because this year I had the opportunity to contribute to those three fields at the same time by providing the first molecular depth estimation in sports video datasets called SoccerNet Depth. In this work, we leveraged the graphic engine from two well-known video games to automatically extract video synthetic depth data from football and basketball. Yes, automatically, because because we used a Python script that autonomously interacts with NVIDIA Inside graphics and the video games. Our script requires only one human interaction when launching it. Then it will continuously analyze the screen, extracting all the necessary information to build molecular depth estimation models. Our process has built a data set of more than 12,000 frames across 74 video sequences that will allow you, the sports video understanding community, to develop temporal consistent research. But to do such research, you will need a baseline. Therefore, we propose a thorough benchmark of a data set with more than 5 state-of-the-art methods completed with 2 models fine-tuned on our data. Those models shows that dedicated training on our dataset improves greatly the performance observed in inference mode. But please feel free to bring the results even further. Our dataset is public and free of charge. So now you might be wondering, is SoccerNet Depth actually useful for real-world application? Well, I'll let you be the judge of this with this slide where our best model has been applied to actual football and basketball footage. So if you're interested or if you want a live demo of our extraction script, please come find us at our cluster.
Thank you, Arnaud. Poster 112. The next speaker is Vladimir from poster 130. 112, sorry.
So let me introduce you to SoccerNet game state reconstruction. So this is another computer vision task that aims to identify and track all players on the court to build a video game-like minimap, as the one you can see here down the video. So more formally, the input to the task is simply a broadcast video, and the output is what we call the game state. So actually, the game state is simply the athlete position on the court through time, together with their role, their team, and their jersey number. And so this task, it holds immense value for the sports industry. But until today, there has been no appropriate open source benchmark for method comparison and for research. And this is what motivated us to introduce our SoccerNet benchmark for game state reconstruction in soccer videos. So with our work, we actually make 3 key contributions. So the first contribution is a data set of 200 videos of 30 seconds each, with all the relevant annotation for game state reconstruction. The second contribution is an open source baseline that is available on GitHub and that we built on top of TrackLab. So TrackLab is actually a multi-object tracking framework that we built with our team. And finally, the last contribution is a novel metric that is called the GS-OTA. And so the goal of the GS-OTA is, of course, to measure the ability of a method to perform game state reconstruction. So this year, we organized the SoccerNet Game State Reconstruction Challenge. And actually, the winning team improved the baseline by more than 40%. So if you're interested in learning more about the winning team, please come back just after the poster session so that we will have their presentation. So thanks a lot for your attention.
The presenter is Robbie.
So good afternoon, everybody. Let me introduce you to our paper about positional analysis and hit detection in padel competitions. So for those of you unfamiliar with padel, it's a bit of a brainchild between tennis and squash. So you can use the wall or run out of the court or whatever you'd like. And it's also a fast-paced racket sport. So when you go to a trainer in padel, one of the first things that you will learn is about keeping an optimal distance between both players of your team. It not only allows efficient communication during the rally, but you can exploit the opponent's defense while minimizing your own vulnerabilities when the ball returns to your half of the court. So non-automated analysis of these distances between players during important moments in the rally, like just before a hit, are often subjective because they are loosely annotated by the coach or too labor intensive to capture for like the full game. So we were working towards an automatic system who does this for a full rally. So as with many problems, we started with creating a new data set, which we will, which is open source. So it includes 5.5 hours of padel rallies with, for each hit, the timestamp annotation, as well as for a subset, whichever of the 4 players hit the ball. Our workflow is completely end-to-end, which means that if you inputted a complete video fragment of the rally, it will use a sound-based hit detection model based on convolutional recurrent neural networks, which is a vision technique applied to the spectrogram of the audio signal. And then it will use a custom player ball tracking mechanism with our own re-identification mechanism to do a hit association with one of the 4 players. And we've also included a somewhat larger feasibility study on combining audio and video features to assign every ball to each player. So the goal of the system is for each hit that you can translate the image above to the one on the bottom and measure all the relevant distances to maintaining the optimal distance between the players of the teams. Thank you.
Next speaker is Tomohiro.
Thank you. Hello, my name is Tomohiro from Nagoya University in Japan. My research focuses on the pose estimation for the daily motion analysis. In the conventional pose estimation, the monocular pose estimation is convenient for daily use. However, its accuracy is insufficient for sports motion. On the other hand, multiple pose estimation is very accurate, but it requires significant resources. For example, many equipment, manual calibration, and more. In our research, we propose an affordable and effective motion capture. We use multiple pose estimation based on automatic camera calibration to fine-tune the monocular pose estimation model for sports motion. After fine-tuning, we can choose between monocular or multiple estimation depending on the situation. Here are the details of our methods. We first estimate the 3D key points from each video, and then we automatically calibrate the cameras using these key points. Finally, we use triangulation results from each view as pseudo-labels to fine-tune the monocular pose estimation model. We can fine-tune the model using pseudo-labels because these labels are more accurate than the result from monocular pose estimation. For example, as shown in the animation, we could improve the pose estimation performance for various sports motion. If you are interested, please visit my poster. Thank you.
Next speaker is Mark.
So good afternoon, and let me introduce you to sports field registration by leveraging geometric properties. We all know about the importance of camera calibration for sports, concretely in soccer, for this 2D motion projection, for the tracking data, or scene reconstruction. But if we're working with broadcast settings, there are things to be aware of. For example, the multiple camera views and the partial occlusion of the code. To solve that, we basically introduce a key points grid, which is composed by 5 different key points sets. Each of them is retrieved by using different geometric properties of field or geometric objects. We propose 2 different pipelines. The first is the training data generation pipeline. We gather the SOCONET calibration annotations, and we hierarchically compute all the previous key points by using geometric validation in all the steps. And then we have an inference pipeline. We basically train 2 encoded decoder networks to extract the generated key points and the line extremities. We merge those 2, and we finally do the camera calibration as a PMP problem. So our main contribution is a calibration pipeline that allows for the multiple views of the broadcast. We set the state-of-the-art in 3D calibration, which is the camera parameter estimation in the SOCONET benchmark and the World Cup 2014. And we also set the more or less the state-of-the-art for 2D calibration, which is homography estimation in the World Cup 14 and the time sequence World Cup data sets. And that's it. I'll be glad if you come back to the poster session. Thank you.
Next speaker is Florian.
Hi, I'm Florian Majara. I work for EVS Broadcast Equipment, and I'm also a PhD student at the University of Liège. So in this work, we present a universal protocol to benchmark camera calibration in sports. So camera calibration is the key to unlock many cool applications related to game analytics. And sometimes such applications, such as briefing ones, require a very high precision. However, in the current benchmarks for camera calibration, the metrics and annotations, they rely on homographies, which have several limitations. So first, homographies are unable to capture lens distortion that are present in broadcast cameras, and also they restrict the evaluation to the sports field frame. This is why we propose another benchmark, which is based on another annotation type, where simply we annotate sparse points along sports fields elements that are semantically identified. And further, we propose another metric, which is a Jack metric, which is based on the reproduction error and which measures the ability of the camera parameters to reproduce the sports field elements in the image. As a result, according to our benchmark, we show that indeed the previous homography annotations lack some precision, and we also validated our benchmark on the SOCONET camera calibration challenges. Thank you.
So for those that were here this morning, this is going to be a bit of a deja vu. So my name is Thomas Broussard, and I worked on table tennis ball spin estimation with an event camera. So with a short introduction of what event cameras are. Event cameras measure changes in the luminosity in a synchronous way, which gives them a high temporal resolution. There's also no redundant data with like static backgrounds, and it has a very high dynamic range. And this is very helpful for us for table tennis, since with event cameras, we don't have any motion blur. So our objective is to use the event cameras to generate the optical flow of an image and like of the ball surface, and from there to extract the spin. So it's just a geometrical problem. And like our setup is with an event camera that's looking top-down view of the table tennis table. And this is just a small video that shows the whole pipeline. Oh, yeah.
Sorry, we ran some technical issue before, but we're gonna fix it right now. Okay.
This is the event representation as in the accumulated event frame. We use a specific representation that's called eros and track the ball using a half circle transform. And this is the extracted events of the logo spinning on the ball. And thanks to this, we can run an inference for the optical flow, and from the optical flow, extract the spin of the ball. So with this whole pipeline, we can run the spin estimation in real time. And this gives us for our benchmark ball spinner really good results. Unfortunately, when we test it with the flying ball, we observed that for balls with slow spin, the frame approach works better than the event approach, but for high ball spins, the event approach is better. Thanks for your attention.
Next speaker is Atom Scott.
Okay, hello everyone. I'm going to be presenting our work on Team Track. So current data sets available for tracking are not quite sufficient enough for tracking in team sports. So as you can see, data sets like Dance Track, Sports MOT, SoccerNet tracking are really great data sets. They're sufficient in size, but they're limited due to camera movement and the specific sports. And the specific sport. So Dance Track only has dance. Sports MOT has soccer, basketball, and volleyball. The SoccerNet tracking only has soccer too. I'm also thinking about the limited camera movement, because a lot of applications in down market would have like fixed portable camera, like VO or studio, things like that. So it would also be nice to have a data set which contains full pitch videos. So that's exactly what we did. We created full pitch, high resolution videos for soccer, basketball, and handball, and high resolution as well. So this is quite a large data set with a lot of frames and a larger bounding box count than previous data sets. So hopefully this will play. Yes. So here's a video. The data set is the one on the bottom, and on the top I'm just showing the whole pitch in like an automatic zoom, so you can see it better. So we have multiple angles for each sport, mostly fixed. There's a bit of movement because we're using drones in a top view angle, but it's mostly fixed and shows the whole pitch. Okay, so we know that. And then finally, so strengths of our Team Track data set is that it's full pitch, multiple sports, large scale, with multiple views, but there was some limitation. There's not a large variance in avenue, and we haven't added jersey numbers, so it doesn't work with GS Hotel just yet. That's what we're working on right now, and we hope we can help the community work on full pitch videos as well. So thank you very much.
Next speaker is Magnus.
Thank you. Hello. I'm here to talk to you about our work on forecasting in badminton rallies. And this is a task that shows great potential both for player analysis, but also game strategy planning. And we found usually that relying only on the sequence alone was quite limiting for sports such as badminton, because each stroke in badminton is tied to a very specific motion. So by incorporating that, and conditioning the rally on that, our proposed model improves this prediction accuracy. And this is done by, for each stroke in the rally, we take a chunk and extract that chunk for the stroke and extract the skeleton data. And then in our proposed encoder-decoder model. These stroke sequences of the skeleton data is through both spatial and temporal attention. A motion representation for each stroke in the rally is captured, which is then in the decoder module through cross attention used to contextualize and provide additional information in order to make the future predictions. And this we evaluated this on two different badminton data sets, where we showed that by adding additional context, also the player-specific ID and also the ground position of the players, we're able to improve the forecasting accuracy of the model, and also comparing to other potential baselines showed great promise. And if you'd like to hear more about this specific architecture or have any questions, please come and visit the poster.
Next speaker is Bruno.
Hello, I'm Bruno, and I represent a paper assessing spotting transfer capabilities across diverse domains. Our motivation was primarily to study the dataset bias that have the SoccerNet dataset, since they have only professional broadcasted matches, and also see the transferability of the currently state-of-the-art methods in other domains. So why? Because if we can do that, we can export this knowledge to other scenarios like amateur games and other ones. So we create a novel benchmark that evaluates 4 different scenarios, since the soccer ones to the eye-piloted cameras and amateur leagues. So we assess the ability to these amateur leagues and these difficult eye-piloted cameras. The conclusion of the work was that the model excels in SoccerNet, but not works pretty well in the other leagues. So we think that more research is needed to enhance the AI robustness in active spotting for can use it in other scenarios. And also we think that the domain adaptation and transfer learning are crucial, because we have no time to train all the models all the time when a new field is coming. So if there are questions or wants to see the results, let's see at the poster session.
Next speaker is Arthur.
Thanks. Okay, so hello everyone. I'll present TD, temporal discriminability and answer encoder-decoder for precise event spotting in a sports video. So this method focuses on 4 main points. First of all, a task that we want to solve, then a set of challenges that we want to address, an architectural solution to try to address these challenges, and finally, the evaluation of this method. So first of all, precise event spotting. If you know the SoccerNet challenges, you will probably know what it is about, but it consists on accurately localizing events represented by single hit points on videos, and with really small tolerance with just 1 or 2 frames. And we evaluated in 2 different data sets. I don't know why this doesn't show as it should, but there is an example of the task. So first of all, the challenges that we find on this task is the need of discriminative per frame representations that we try to solve introducing the model to promote discriminability between adjacent frame representation, then the necessity of high output temporal resolution, which we try to solve by an encoder-decoder architecture, and the variability in the amount of temporal context that is required depending on the different actions. And we use different temporal scales to try to solve that. So the proposed solution is the one shown in here, which has three main parts. First of all, a figure extractor to obtain per frame representation, then a temporally discriminant encoder decoder to try to model the temporal information, and finally the prediction head. And if you want to know more details about that, you can come to the poster session and I'll explain that. And finally, the results, we obtained the state-of-the-art result on two different data sets and three different configurations on the fine diving and figure skating data set. And if we had a bit more of time, I would show you a bit more detail, the qualitative results that we obtained on the two data sets. But just to let you know also, as this workshop mainly contains soccer as its main sport, we also adapted the model to the soccer net challenges on the ball action spotting data set, obtaining quite good results. And yeah, that's all. Thank you. Yeah.
I think our last speaker is Ahmed. Sim. Oh, Asim. Are you Asim? Okay. Yours. Thank you.
Good afternoon, everyone. My name is Asim. I'm a co-founder of Disney Technologies. It's a one-month-old startup in Seattle. I'm also an adjunct professor of multimodal AI at Cornell. So far, we have been looking at a lot of interesting data sets and problems with soccer. And as much as we all love soccer, what we don't love is like see our best players getting injured. So what do we do when they get injured, right? Much like so many personalized recommendation systems, we like to introduce something called personalized recommendation rehabilitation therapy. And the way we achieve this is, imagine we have key points of different joints, as you can see on the left. And then we take this data of key points, we can feed it to a simple classifier, just like a random forest classifier. And we have a downstream cast of a healthy and an unhealthy. So when we train this model, we can actually look at the ranking of each joint that participates in classification. So once we have that, we can rank them, as you can see, those color-coded joints. We take the same information, we feed it to a VQVAE, which is a very powerful high to low dimensional mapper. We train this model on those key points, and then we look at the latent space, and we just project it into a 2D plot. We have each key point green as healthy and red is unhealthy. And we can find the centroids of those clusters. Once we do that, then we can find which of these joints, essentially the minimum number of joints, that can give us the best performance in terms of like separation between healthy and unhealthy. So once we have that, we can actually project it in terms of like high joint importance to a low joint importance, and have a very personalized recommendation for a sports injury, right? So we ran this on a variety of exercises, essentially 9, using IntelliRehab as data set. And as you can see, for different exercises, depending on which limb is affected, whether it's arm or it's leg, our recommendation system is able to precisely give like the top 2 joints, which one should actually use to modify to have a very efficient rehabilitation. I'm at poster number 123. Would love to catch up. Thank you.
Thank you for your attention for those presentations. That concludes.
We got everything working. Thank you very much for coming back. Hope you all had a wonderful poster session with lots of discussion and maybe collaboration opportunities in the future. So now we're going to move to the SoccerNet Challenge results announcement part of this presentation. So we will take 15 minutes to present you the winners of the 4 challenges that we organized this year with SoccerNet, and also present the first place method by the authors who sent us videos. So let's just give you a bit of general information on the challenges in 2024. So we had 4 tasks. that we're going to present each of us. And then we had 7 coordinators for these different tasks and 4 sponsors who provided a total of $4,000 of prize, so $1,000 per challenge. So the challenges ran from February 1st to May 30th. And this SoccerNet challenges that we organize are actually a very unique model where you have open source data, open source methods, benchmarks, and so challenges that we organize around. So we're really proud to present you this today. So just for those of you who didn't know, this is actually the 4th edition of the challenge that we presented at CV Sports every year since 2021. And this is all thanks to our wonderful team coming from the University of Liège, KAUST, but also UC Louvain in Belgium, Aalborg University in Denmark, EPFL in Switzerland, and a lot of our industrial collaborators who help us organize the challenges like Baidu Research, EVS Broadcast Equipment, Sportradar, NASC Science, and also two other universities, so University Libre de Bruxelles and the FNRS. So this is the team that provides you with the organization of all the challenges, but actually SoccerNet is much more. So we don't only just organize tasks, we also do a lot of collaboration with different entities from all around the world, like FIFA or the Saudi Pro League, Photovision, Speedio. So these are all of our partners with who we collaborate. And basically, SoccerNet is also you, right? The participants. So if we take a look a bit at the national interest of our data set, we can see that, well, we've got almost 100,000 visits from 187 countries. So that's basically all countries in the world who are now interested in our data set and downloading it. And you may be aware of it, but we also have a Discord community where we try to gather all these researchers and industrials who are interested in computer vision in sports. And now we're really proud to say that our community has grown a lot this year with more than 1,050 members in total. So if you haven't joined already, feel free to go on our website and just join our Discord. It's a really great forum where you can discuss, find partners to participate in the challenge with. For those of you who don't know, we also got a YouTube channel where there are some tutorials to get started on the different tasks. So we've got a lot of videos there. So feel free to just go and check them out if you want to get started in one of the challenges. And so finally, a few numbers from the previous edition of the challenges. So in total, we got before 2024, 100,200 submissions from 134 teams in the world. And it's mostly half-half academia and industry. And so for this year, these are the new numbers. So we got different teams participating in either the test set or the challenge set to be eligible for the prize. And I'm going to focus mostly on the challenge set numbers. So 42 teams in total who participated in one of the 4 challenges with more than 115 submissions. So just to put these numbers into perspective, each team received 2 or 3, depending on the challenge, number of submission per month. So this is why this number is almost 2 or 3 times. Now, these challenges wouldn't be the same without our sponsors who are providing prizes for the winners of the task. So I want to thank them. So Science NASC for sponsoring the Ball Action Spotting Challenge, Quality for sponsoring the Dance Video Captioning Challenge, TIA Technology for multi-view file recognition, and finally Sportradar, who is also here with us today, for sponsoring the game state reconstruction. So now we're going to move on to the announcement of the first challenge winners for the first half of Ball Action Spotting. So for those of you who don't know, Ball Action Spotting, the task consists in precisely localizing when and which soccer action related to the ball occur. And usually this is within a 1 second precision that they have to say, okay, there is for instance, a pass, a drive, a high pass, a cross. So across 12 different kind of events. And so here with this data set, we wanted to see, can we overcome low amount of data? So not having to annotate 500 game like in the SoccerNet original action spotting challenge, but more like with only 9 games, can you transfer knowledge to actually get good performance on different events? So a bit like for the Kings League, that could be something very interesting. So let me just first play the video of our sponsor, so Ask Science. So there is no sound, I think there should be. Yes, it's just very low. No. All right, so thank you, Ask Science, for sponsoring this challenge. So now let's have a look at the leaderboard. So the number one are masks at the moment, but you will know it is in just a minute. So let's take a look first at the numbers there. So we started the baseline, which is a average precision at 1 second tolerance, which was around 56.15. And so the first one got, drum roll, Arthur, who is here in the audience, actually. So congratulations to him. You're there. Congratulations. So with a stunning 73.39 MAP at 1, which is an amazing result. And so he prepared a video of how he actually did it, but you already got some information during the workshop. So let's see his presentation.
Hello everyone, I'm Artur Charles from Universidad de Barcelona, and I'll present our method, TDIT, to solve the task of ball action spotting, which is in collaboration with Sergio Escalera, Thomas Mueslum, and Albert Clapes. In this paper, we adapted TDIT, which is a method that we presented in this workshop, and I hope that you could see it on the poster session. And basically, it addresses 3 main challenges that we found on the task, which is the need for discriminative per frame representations, the necessity of high output temporal resolution, and finally, the variability in the amount of temporal context that is required depending on the actions. This is the main architecture of our model, which it has 3 parts. First of all, a feature extractor to obtain per frame representation, then a temporally discriminant encoder decoder to process the temporal information, and finally a prediction head to produce the final predictions. As we observed that SoccerNet is a small data set, we also make use of the original and larger data set of SoccerNet, and we do so in a multitask training way, in a way that we have 2 different predictions heads, one for each of the data sets. And we process videos in clips of 8 seconds and with the shown resolution and frame rate. Finally, we produced the final predictions as an ensemble of 2 different TDIT models using different sampling techniques. We obtained 73.39 map on the challenge split, and here we can see some results of our method on the challenge split.
So let's congratulate him again. And if you can come up and take a picture with you. Yeah, of course. I didn't know you were there. So here it is. Let's maybe just, yeah. Congratulations. Thanks. Awesome. Congrats. All right. So what were the novelties this year outside of course, the great method of Arthur that we just saw? Well, actually, so people have been leveraging the SoccerNet dataset to improve for the SoccerNet ball action spotting. Which is great, which is what we wanted to see. And also some people did some multitask learning, so different prediction head for the different data sets, and this also helped the method reach better performances. And finally, some more training techniques like dynamic sampling or combined loss calculation also have helped a lot the different methods reach higher performances. So now we leave the floor to Silvio, who will present the dense video captioning task and the winner.
Right. So the dense video captioning task was sponsored by Quality. So what is the dense video captioning task? The task is basically to generate anchored commentaries of a football soccer game. So the data was composed of 500 broadcast games, and the type of annotation that was provided are textual commentaries that are anchored at a single timestamp. So typically an approach would actually try to first localize when to actually provide some commentaries and then generate some textual commentaries that would describe the scenes like you can see on the left. This task has been sponsored by Quality. I have a presentation of the company here. Sorry. Technical issues, sorry about that. Getting used to it. Here we go.
Tell me who's best, cause I know it's only one. The shoes on my feet, the blood that I bleed, the game is only begun. We do, and we're doing it. You like that and feel we don't think that's wise. Watch the way going round and in your lives.
Right. We thanks Quality for the sponsoring of that particular task. Back to the presentation. So we didn't have like many participants to that task because first of all, it's quite a difficult task to generate language and first anchored on them. It's first finding the anchor where to generate them. We had 3 participants. 2 of them improved upon the baseline. And the first one, drumming rolls, is Jamshid Tursunobers. I hope the pronunciation is fine, from the Delta Lab. Unfortunately, Jamshid is not here in the room, but congratulations to him. Here is a presentation of their method.
This is Delta team. This presentation is solution for SoccerNet 2024 dense video captioning task.
Here's our model architecture. Our model consists of 2 parts. First is a visual encoder that consists of 4 transformer decoder layers that takes 8 query tokens and the visual features as an input. And the outputs of that layer fits into the LLM. In our case, it's GPT-2, and it outputs the captions. It's important to mention that both parts are fully fine-tuned end-to-end, including the GPT, without using any frozen weights.
We tested multiple threshold values from 0.5 to 0.75. We picked best value for test data set. When the threshold is greater than 0.7, the model's performance is graded immediately.
Yeah, here's our most impactful contributions. The most important one is end-to-end training the model, including the LLM, without freezing the LLM weights. And the second is changing the spotting action task from binary to multi-class softmax classification so that the model outputs the confidence levels for each task separately. Thank you.
And congratulations to them again.
This is Delta.
All right. Well, most of the contribution was basically from the LLM that they built. Next, I'm going to leave it to Jans to present the result of the multi-view file recognition.
Thank you very much, Silvio. I will present you the multi-view file recognition challenge, which was sponsored by Thea Technology. So the task was very, let's say, simple. You just have to put yourself in the shoes of a referee. You have to determine if it is a foul or not, the severity of the foul, and the type of fouls. For example, if it was a tackle, holding, or pushing, for example. Now let's have a look at the sponsor of the challenge, Thea Technology. Thank you very much for Thea for sponsoring the challenge. This year we had 17 teams who participated at our multi-view foul recognition challenge, where actually 6 of them beat the baseline that we have built and presented last year here at CB Sport, and some of them really beat the baseline by 6 or even 7 and 8%. And now let's have a look at the first place. And it's Ying Zhang from Intelligent Perception and Image Understanding Lab from the Xidian University. Now let's have a look at their video when they explain how they actually achieved this result.
Hello, everyone. My name is Zhong Jing, and I am from Xidian University. Today, I am excited to present our team's participation in the Multi-View Foul Recognition Challenge. Our team includes my colleagues Lu Xinyu and Zhong Kersen. We adopted several methods to achieve impressive results in this competition. Firstly, let's talk about our backbone. We used ViTB, a robust architecture that provides a solid foundation for our model. For initialization, we utilized the pre-training weights from a foundation model known as the unmasked teacher. This allowed us to leverage pre-existing knowledge and enhance our model's performance from the start. For feature aggregation, we adopted a straightforward yet effective technique, max pooling. This method efficiently condenses the information from multiple views, allowing us to capture the most relevant features for classification. The final step in our approach is the classification head, where we employed MLP. This component processes the aggregated features and outputs the final classification results. After implementing these strategies, our model demonstrated outstanding performance in the challenge. Specifically, we achieved a final score of 44.76, placing us among the top performers in the competition. Notably, we also experimented with using Uniformer v2 and VIT v1b as the backbone networks. However, we found that these alternatives did not perform as well as our chosen approach. In summary, our approach, utilizing ViTB as the backbone, pre-training weights from the unmasked teacher, max pooling for feature aggregation, and an MLP for classification proved to be highly effective. Thank you for your attention.
But we also had a lot of different other novelties. There were a lot of people who experimented with the number of frames they use to do the classifications. Some of them use like 16 frames, some of them use like 50 frames. And also some of the participants used the backbone of visual language model architectures to make the classification prediction, which also works quite good. Some of them also used smaller models in order to use image input with a higher resolution, and instead of using the 224 resolution, going up to 720. Some also try to incorporate multiple context windows, for example, not just the foul on itself, but also taking some seconds before the foul or some seconds after the foul. Now I will give the floor to Victor, who will present the last challenge.
Thank you, Jan. Let me introduce you to the game state reconstruction challenge. And so basically, as Vladimir already explained extensively to you, this task is very simple. You go from an input broadcast video, and what you have to show is an output minimap with the jersey number of all the players, their role, and their team. I won't go into much detail, and so let me introduce you to this task sponsor, Sports Radar.
Thanks. The video doesn't have audio, unfortunately, and that's why I'm speaking. And yeah, the idea is to present Sports Radar is like a company that is present in, I guess, 19 countries with more than almost 4,000 employees. We spread across different sport solutions, from, of course, creating the odds for betting, but also AI and broadcast and augmented streaming technologies, but also integrity services to determine, for example, if matches are set or not. So there are many solutions we offer. Yeah, I hope that our contributions was appreciated. Thank you. Bye.
Thank you, Davide, and thank you, Sport Radar, for sponsoring this task. Let's now look at the results. No. Yes. And as you can see, we had 15 teams that participated to this challenge. And yeah, most of them beat our baseline, and most of them beat our baseline by huge amounts. But let's look at the first place, which is Constructor Tech, which is a team that was led by Vladimir Golovkin from the Constructor Tech company. Congratulations to them. Let's now look at how they did it.
Hello, everyone. We are the team from Constructor Technology Sports Solutions. In this short presentation, we want to show our solution for SoccerNet Game State Reconstruction Challenge 2024. The whole pipeline consists of 3 steps: team detection, raw tracking step, and post-processing step. On this step, we detect 5 clusters: left-right team athletes, referees, left-right goalkeepers. For all detected athletes, we calculate pitch coordinates and team embedding. Then we estimate 3 embedding clusters and calculate mean X coordinate for them to detect left team from the right. Then we detect goalkeeper clusters from objects inside penalty area and filter objects from previously found clusters. At this stage, raw tracking is performed. This process consists of 2 main parts: pitch localization and objects detection. For all detected athletes, we calculate re-ID embedding, player orientation, team ID, jersey number, if any. All networks are relatively straightforward, except for the jersey number model. It has 2 output heads for each digit in jersey number. For tracking algorithm, we use deep sort operating in pitch coordinates instead of bounding boxes and with a few restrictions based on player orientation and team ID. As the last stage, we refine and concatenate tracklets into longer tracks. We ensure continuity by matching tracklets start and end times, re-ID embeddings, team ID, jersey numbers, and player speed. Thank you for attention.
Let me now quickly summarize some of the novelties that the team displayed for the game state reconstruction task. So basically, most of the teams modified at least 3 modules, which were the athlete detection module, the camera calibration module, and the jersey number recognition module. Most of the teams simply fine-tuned the athlete detection detector on soccer data instead of what we used on the baseline, which was a simple Coco trains athlete detector. And one team did row classification with the object detector. But most of the improvements probably came from the camera calibration and jersey number recognition modules, where for the camera calibration, one interesting fact is that one of the teams used their own method that they published here at CV Sports today, no bells, just whistles. And the module that had the most diversity in different approaches was the jersey number recognition module. There you go.
All right. Thank you very much. So for those of you who are in top 1, 2, 3, and who are here today, so Mark is there somewhere. Yes, over there. Come get your certificates. We'll take a picture also afterwards. Otherwise, yeah, just to conclude on the SoccerNet challenges, once again this year it was a huge success. So thank you very much to all participants for making this competition so alive. So 42 teams, half academia, industry. We also I want to thank all the task organizers who are here today, but also who could not attend. Without them, of course, it would be impossible to organize all these tasks. Of course, many thanks to our 4 sponsors for providing the prize money, and also to the CV Sports organizer who've been more than supportive for the past 4 years with the SoccerNet challenges. And this is also thanks to them that we have this great challenge. So yeah, let's give them, everyone, a big round of applause. And now we will move to the very last section, the Best Paper Award announcement. So we will announce the 3rd, 2nd, and 1st place for the Best Paper Award of CV Sports. So if you see your name on the screen at some point, please come take a picture with us. Let me just try to get the presentation that is thing behind. All right. There we go. So yeah, for the Best Paper Award, many thanks to Sfera for sponsoring this challenge, this Best Paper Award, still in the challenge. So how was the selection process made? Well, the oral papers were already selected based on review scores, and also we read the reviews, read the papers, and we figured out that, yeah, these papers deserved also to be shown during oral presentation. If we had more time, we would have taken much more papers. To be honest, there were so much great papers this year. It was very hard to select. Then, based on these 5, there was a jury composed of the CV Sports organizer who read all 5 papers without looking at names or anything, except for conflict of interest. So basically Silvio and I, who were not part of the selection process because we have a lot of papers here. And also some scores were given for the presentations today. Everything was aggregated, and the committee of CV Sports, except the 2 of us, gathered to say who was the top 3 papers. So without further ado, I think we can start with the 3rd place. So even-based ball spin estimation in sports by Takuya Nakabayashi. So congratulations to them. And they can come up front and take a picture.
Thank you. Congratulations. Congratulations.
All right, now for the second place. We have XVARS, introducing explainability in football refereeing with multimodal large language model by Jan Held. Congratulations to him. And now the moment you've been waiting for, and I will ask also Mirko to come for giving the Best Paper Award, which is given to Lauren Okamoto for hierarchical neurosymbolic approach for action quality assessment. Very great work, to be honest, and great presentation as well. It was noted by the jury. So congratulations.
Congratulations. Congratulations. Congratulations. Congratulations. Go. Oh, you have enough space? Yeah.
Awesome.
Congratulations.
All right, so now it's time to conclude. So thank you very much for attending this 10th edition of CV Sports. It's been a great event, a lot of great presentations. So thank you to all presenters, all participants as well, who you asked very good questions. I think it was very interactive this year. And yeah, see you at the social event of Sport Logic. And if you want, we can take a big group picture, maybe all together, all attendees who want to be in the picture. That would be great. Thank you very much.